Our sun is a dwarf. We call it average. We call it normal. We teach children it's a middle-sized star in a middle-aged galaxy. And for most purposes, that's true enough. But there are objects in this universe so catastrophically large that if you placed one where the sun sits now, its surface would reach past Jupiter, past Saturn, so far out into the void that light itself would take hours just to lap its circumference once. These are the hypergiant stars, the monsters, the objects that sit at the bleeding edge of what physics will allow. And the deeper we look, the less sense they make. Scuti is 1,700 times wider than our sun. WOH G64 may be larger still, a red behemoth wrapped in its own funeral shroud, bleeding mass into space faster than we can measure. And then there's R136A1, a star so massive it violates the theoretical limits we thought governed stellar formation. It weighs in at nearly 200 times the mass of the sun, burning so violently that it should have torn itself apart millions of years ago. And yet it hasn't. It's still there, still fusing, still defying the math. The question isn't just how big a star can get. The question is why the universe allows them to exist at all. Because according to the equations, stars like this shouldn't form, they shouldn't survive, and when they die, they don't go quietly. They take entire regions of space with them, carving out voids, seeding galaxies with the raw material for worlds, for life, for everything that comes after. This is the story of the largest stars we've ever found, the physics that makes them possible, the chaos that tears them apart. And what happens when something so immense that it bends the rules of reality finally runs out of time? Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Our sun is a monster, by human standards anyway. Take Earth, the only planet in the known universe where anything resembling your daily commute has ever occurred, and compress it down to the size of a marble. Now imagine stacking marbles, not a handful, not a truckload, 1.3 million of them. That's how many Earths you could pack inside the sun if you had the patience and a criminal disregard for the laws of physics. 1,300,000 Earths, lined up side by side. That's enough to stretch from here to the moon and back more than 17 times. The sun is not a small object. And yet, by the standards of the universe, by the standards we're about to walk through together, the sun is unremarkable. It's not tiny, it's not embarrassing, it's just average. If you took all the stars in the Milky Way, threw them into a hat, and pulled one out at random, you'd probably get something pretty close to our sun. A yellow dwarf, a main sequence star. The kind astronomers catalogue with a shrug and move on. It weighs about 330,000 times the mass of Earth. It burns hydrogen into helium at a rate of about 600 million tons per second. It has been doing this for roughly 4.5 billion years. It will keep doing it for another 5 billion. It is stable, predictable, and utterly typical. We are orbiting mediocrity, and mediocrity has kept us alive. That mediocrity is still difficult to wrap your head around. If you could somehow stand on the surface of the sun, which you could not because you would vaporize long before you got close, the horizon would curve away from you at a rate so gentle that you'd think you were standing on a flat plane. The surface area of the sun is roughly 12,000 times the surface area of Earth. You could walk in a straight line for years and never notice you were going in a circle. The sun contains 99.86% of all the mass in the solar system. Everything else, All the planets, all the moons, all the asteroids and comets and dust grains drifting between the orbits, every single rock we've ever landed a probe on or pointed a telescope at, adds up to a rounding error. Jupiter, the largest planet we have, the one with a mass 318 times Earth's, is still only 1,000th the mass of the Sun. If the Sun were a bowling ball, Jupiter would be a marble. Earth would be a grain of sand. And this is the baseline. This is the unit astronomers use to measure other stars. They don't say a star weighs 4.2 times 10 to the 30 kilograms. They say it weighs 2.1 solar masses. They don't say its radius is 696,000 kilometers. They say it's one solar radius. The Sun is the yardstick, the reference point, the thing every other measurement pivots around. When astronomers want to describe something bigger, they describe how many suns you could fit inside it. When they want to describe something hotter, they compare it to the Sun's surface temperature of about 5,500 degrees Celsius. The Sun is not special, it's just ours. And because it's ours, it became the ruler we use to measure everything else. For most of human history, we had no idea how big the Sun was. We knew it was bright. We knew it was hot. We knew staring at it was a bad idea. But size? Distance? Actual physical dimensions? Those were guesses dressed up in philosophy. The ancient Greeks took a swing at it. Aristarchus of Samos, working around 230 BC, tried to calculate the distance to the Sun using geometry and the angle of the Moon during a half-lit phase. His method was sound, his instruments were not. He got a number that was about 20 times too small, but the fact that he tried at all, the fact that he understood the Sun was far enough away that geometry could be applied to it, was a leap that wouldn't be properly followed up on for nearly 2,000 years. By the 1600s, astronomers had better tools and a more urgent problem. If you wanted to navigate a ship across an ocean without dying, you needed to know where you were. And if you wanted to know where you were, you needed accurate star charts. And if you wanted accurate star charts, you needed to know how far away the stars were. The Sun was the closest one, so it became the test case. In 1672, Giovanni Cassini and Jean Richer conducted one of the first successful parallax measurements, using observations of Mars from two different locations on Earth to triangulate the distance to the Sun. They got it wrong, but only by about 7%, close enough to matter, close enough to realize the Sun was not hovering just past the clouds. It was sitting roughly 150 million kilometers away, give or take, and at that distance, for it to appear as large as it did in the sky, it had to be enormous. The next question was what it was made of. For a long time, the answer was coal. Serious scientists in the 1800s genuinely believed the Sun was a giant lump of burning coal, radiating heat the way a fireplace does, just on a much larger scale. The math didn't work. If the Sun were made of coal and burning at the rate necessary to produce the observed brightness, it would have exhausted itself in about 1,500 years. Geological evidence already suggested Earth was far older than that, so coal was out. Then came the idea that the Sun was powered by gravitational contraction. As it slowly collapsed under its own weight, it would heat up and radiate energy. That bought you a few tens of millions of years. Better, but still not enough. Fossils and rock layers were telling geologists that Earth had been around for hundreds of millions of years at minimum. The Sun had to have been burning for at least that long. The actual answer didn't arrive until the 1920s and 30s, when physicists finally worked out the mechanics of nuclear fusion. Hydrogen atoms, under enough pressure and heat, smash together and fuse into helium. In the process, a tiny bit of mass is converted into energy. That's what Einstein's equation was telling everyone. Mass and energy are the same thing in different forms, and the conversion rate is obscene. 1 kilogram of matter, if you could convert it entirely into energy, would release about 90 million trillion joules, enough to power the entire United States for several days. The Sun is converting 600 million tons of hydrogen into helium every second, and it has enough hydrogen left to keep doing that for billions of years. Finally, the timeline made sense. By the mid-20th century, astronomers had a working model of what a star actually was. A ball of gas held together by its own gravity, with a core so hot and dense that nuclear fusion runs continuously, producing enough outward pressure to keep the whole thing from collapsing. The balance between gravity pulling inward and pressure pushing outward is what keeps a star stable. Tip the balance one way and the star swells, tip it the other way and it contracts. That balance is also what determines a star's size, brightness and lifespan. And once astronomers understood that, they started classifying stars not by mythology or which constellation they happen to sit in, but by measurable physical properties. The system they landed on is called the Hertzsprung-Russell diagram, named after Edna Hertzsprung and Henry Norris Russell, who independently developed the idea in the early 1900s. It's a graph. On one axis, you plot a star's temperature. On the other, you plot its luminosity, meaning how much light it actually produces. When you plot thousands of stars on that graph, they don't scatter randomly. They fall into patterns. Most stars land on a diagonal band running from the top left, hot and bright, to the bottom right, cool and dim. That band is called the main sequence, and it's where stars spend the vast majority of their lives. Our Sun sits almost exactly in the middle of it. Not the brightest, not the faintest, not the hottest, not the coolest. Average, but not every star sits on the main sequence. Some sit above it, in a region where stars are far brighter than their temperature alone would suggest. These are the giants and supergiants. They've burned through the hydrogen in their cores and moved on to fusing heavier elements. In the process, they've swelled to enormous sizes. Their surfaces are cooler, which is why they glow red instead of yellow or blue, but their sheer size makes them incredibly luminous. A red supergiant can be 1,000 times wider than the Sun and tens of thousands of times brighter, even though its surface is only half as hot. Then there are the hypergiants. These sit at the very top of the diagram, so bright that for a long time astronomers weren't sure objects that luminous could even be stars. Some of them pump out more light in 6 seconds than the Sun produces in an entire year. Their surfaces are so far from their cores that gravity barely holds them together. They shed mass constantly, blowing off outer layers in slow motion, surrounding themselves with clouds of gas and dust that can be larger than our entire solar system. These stars are not stable. They flicker, they pulse, they dim and brighten over timescales of months or years, and they do not last long. A hypergiant might live for only a few million years before it runs out of fuel and detonates. The Hertzsprung-Russell diagram is more than a classification tool. It's a map of stellar evolution. Stars are born on the main sequence. They spend most of their lives there, steadily fusing hydrogen into helium. Then, when the core runs out of hydrogen, the star's structure changes. The core contracts and heats up. The outer layers expand and cool. The star moves off the main sequence and becomes a giant. How big it gets and what happens next depends almost entirely on how much mass it started with. Low-mass stars like red dwarfs never leave the main sequence at all. They'll still be burning hydrogen trillions of years from now, long after every other type of star in the universe has burned out. Mid-mass stars like the Sun swell into red giants, puff off their outer layers, and leave behind a white dwarf. High-mass stars go supernova and leave behind neutron stars or black holes. And the very highest mass stars, the ones we're building toward in this story, swell into hypergiants so large that the physics starts to break down. Measuring the size of a distant star is harder than it sounds. You can't just point a telescope at it and see how big it looks. Stars are so far away that even through the most powerful telescopes they appear as single points of light. The sun only looks like a disk because it's close. Every other star in the sky, no matter how large it actually is, collapses into a dot. So astronomers have to get creative. The most straightforward method is called interferometry. You take two or more telescopes, space them far apart, and combine their observations. The combined image has the resolving power of a single telescope as wide as the distance between them. If you space your telescopes across a continent, you can theoretically resolve details smaller than the width of a coin sitting on the surface of the moon. That technique has been used to directly measure the diameters of a few dozen of the largest, closest stars. But it only works for the very biggest and the very nearest. For everything else, astronomers rely on indirect methods. If you know a star's distance, temperature, and brightness, you can calculate its size. Distance comes from parallax, the apparent shift in a star's position as Earth moves around the Sun. Temperature comes from the star's color and spectrum. Brightness is measured directly. Plug those numbers into the equations, and out comes a radius. The problem is that every number in that chain has uncertainty. Distance measurements can be off by 10 or 20%. Temperature estimates depend on models of how stellar atmospheres behave. Brightness can vary if the star is pulsing or if there's dust in the way. So when you read that a particular star is the largest ever found, what you're really reading is the largest according to one team's analysis using one set of assumptions at one point in time. A different team with different data might get a different answer. This is why the title of largest known star keeps changing. For a while it was VY Canis Majoris, then it was VV Cephei, then NML Cygni, then UY Scuti, then back to UY G64, then back to UY Scuti, then Stevenson 2-18 entered the conversation. Every few years, someone publishes a new measurement, a new distance estimate, a new model of a star's atmosphere, and the rankings shuffle. None of these stars are small. They're all unimaginably massive. But which one is actually the largest depends on who you ask and when you ask them. The first real measurements of giant star sizes came in the mid-1800s, not long after spectroscopy gave astronomers a tool to analyze starlight in detail. In 1860, astronomers at the Bonn Observatory in Germany were cataloguing stars in the southern sky when they noted an object designated BD-125055. It was faint, reddish, and sitting in the constellation Scutum. They wrote it down and moved on. Nobody realized what they were looking at. It would be more than a century before anyone took a close enough look to realize that star was not normal. By the time modern instruments finally measured it properly, BD-125055 had been renamed UY Scuti, and it had become one of the most extreme objects ever catalogued. But we're not there yet. The point is that for most of history, we didn't know giant stars existed. We knew some stars were brighter than others. We knew some were redder. But the idea that a star could be hundreds or thousands of times wider than the sun, that you could fit hundreds of millions of suns inside a single stellar envelope, that a surface could be so far from a core that light took hours to cross the gap, none of that entered the conversation until the 20th century, and even then it took decades to confirm. The tools didn't exist, the physics wasn't understood, the measurements were too uncertain. Now we have those tools. We've mapped the temperatures and brightnesses of millions of stars. We've measured distances with space telescopes that don't have to look through Earth's atmosphere. We've built computer models that simulate the internal structure of stars from core to surface, tracking how energy moves, how elements fuse, how pressure and gravity fight for control. And what those models tell us is that stars can get big, astonishingly, unreasonably, almost comically big, big enough that if you placed one at the center of our solar system, it would swallow planets, not metaphorically, literally. The outer layers of the star would drift past Earth's orbit, past Mars, past the asteroid belt, all the way out to Jupiter or beyond, depending on which star you picked. That's where we're headed, to the stars so large that the numbers stop sounding real, to objects so far outside the human scale of reference that the only way to understand them is to stack comparison on top of comparison until the reality finally clicks. But before we get there, we need to clear up a common confusion. Size and mass are not the same thing. The largest stars are not the heaviest. In fact, some of the largest stars weigh less than stars a fraction of their size. That paradox is what makes the next part of this story so strange. Size and mass are not the same thing. That fact needs to be carved into the front of every astronomy textbook because it trips up almost everyone who wanders into this corner of the universe. A star can be enormous, hundreds of times wider than the Sun, and still weigh less than some stars a fraction of its size. That paradox sits at the heart of understanding what stars actually are and why some of them break the rules. Mass is how much stuff a star contains. Size is how much space that stuff takes up. A red supergiant like Betelgeuse, one of the most famous giant stars in the sky, weighs somewhere between 15 and 20 times the mass of the Sun. Not small, but not exceptional either. There are plenty of stars heavier than Betelgeuse. What makes Betelgeuse remarkable is that it has swollen to roughly 700 times the Sun's diameter. If you dropped it into our solar system in place of the Sun, its outer layers would drift past the orbit of Mars. The star is enormous because it is dying. Its core has run out of hydrogen. The internal balance that kept it stable for millions of years has shifted. The core contracted, the outer layers expanded, and now the star is a bloated shell of gas held together by gravity that barely has a grip on the material anymore. The density at the surface of Betelgeuse is lower than the best laboratory vacuum ever created on Earth. You could fly a spaceship through the outer layers and not notice you were inside a star until the temperature started climbing. Now take a different kind of star, a main sequence star like the Sun, but heavier. Say 50 solar masses. That star is not going to swell. Not yet. It is burning hydrogen in its core at a ferocious rate, pumping out energy so fast that its surface glows blue-white. Its radius might be only 10 or 15 times the Sun's. In terms of volume, it is tiny compared to Betelgeuse, but it weighs more than twice as much. It is denser, hotter, brighter, and far more violent. And it is sitting right at the edge of what physics says should be possible. There is a limit to how massive a star can be, not a suggestion, not a guideline, a hard boundary written into the equations that govern how stars work. That boundary is called the Eddington limit, named after Arthur Eddington, the British astrophysicist who worked it out in the early 1920s. Eddington realized that as a star gets more massive, it also gets more luminous. Brightness is not a linear function of mass. Double a star's mass, and its brightness goes up by a factor of 10 or more. That extra light comes from the fusion reactions in the core running faster and hotter. But light is not just light. Light carries momentum. Photons, the particles of light, exert pressure when they slam into atoms. Inside a star, that pressure pushes outward against the gas in the outer layers. The effect is small for a star like the Sun. Radiation pressure contributes to holding the star up, but gravity is doing most of the work. For a much more massive star, radiation pressure becomes a serious force. At a certain point, the outward push from the star's own light becomes strong enough to blow the outer layers away. That point is the Eddington limit. Cross it and the star becomes unstable. The outer layers start getting stripped off by the radiation field. The star loses mass faster than it can replace it. In practice, this sets a ceiling on how massive a star can grow. Build a star too heavy and it tears itself apart before it ever settles into a stable configuration. The theoretical limit sits somewhere between 100 and 150 solar masses, depending on the composition of the gas the star formed from and how fast it accreted material in the first place. Stars near that limit should be rare, short-lived, and extraordinarily difficult to form. They should be. And yet, sitting in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way about 160,000 light-years from Earth, there is a star that weighs 196 times the mass of the Sun. Its name is R136A1, and it should not exist. The star was discovered in the R136 cluster, a dense grouping of young massive stars sitting inside the Tarantula Nebula, one of the most active star-forming regions in the local group of galaxies. The cluster itself is remarkable. It contains dozens of stars heavier than 50 solar masses, packed into a region only a few light-years across. That kind of concentration is unusual. Most massive stars form in relative isolation or in small groups. The R136 cluster looks like a factory that got its production settings wrong and started churning out giants. When astronomers pointed spectrographs at the cluster in the early 2000s, they started sorting the stars by temperature and brightness. One star stood out immediately. It was hotter than anything else in the cluster, brighter than anything else in the cluster, and its spectral lines were so broad and distorted that it took years to untangle what was actually happening. The problem was motion. The surface of R136A1 is not sitting still, it is boiling. Convection currents churn through the outer layers at speeds of hundreds of kilometers per second. Material is constantly being hurled outward by radiation pressure, creating a stellar wind so intense that the star is losing mass at a rate of about 1 Earth every 1,000 years. That wind blurs the spectral lines, making it difficult to measure the star's temperature, composition, and velocity. Early estimates put the star somewhere between 150 and 200 solar masses. Follow-up observations using better instruments narrowed the range. By 2010, the best estimate placed R136A1 at about 265 solar masses. That number made headlines. If it was correct, the star was more than twice the theoretical mass limit. It was not just breaking the rules, it was obliterating them. Then the number came back down. Later studies revised the mass estimate to somewhere between 170 and 196 solar masses, depending on the model used to interpret the data. Still far above the Eddington limit, still inexplicable, but not quite as absurd as 265. The revision did not make R136A1 any less of a problem, it just made the problem slightly more precise. So how did it form? There are 3 leading ideas, and none of them are particularly satisfying. The first is rapid accretion. In this scenario, the star formed in the usual way, from a collapsing cloud of gas, but the collapse happened so fast and in such a dense environment that the star was able to pile on mass faster than radiation pressure could blow it away. Think of it as a race. If the gas falls inward quickly enough, the star can gain mass before its own light has time to push back. Once the star reaches a certain size, the radiation pressure stabilizes and the accretion slows down. You end up with a massive star sitting just below the point where it would tear itself apart. The problem with this model is that it requires very specific conditions. The gas cloud has to be dense, cold, and rotating slowly enough that the infalling material does not form a disk that chokes off the accretion. Those conditions are not common, and even when they do occur, simulations suggest the star should still struggle to get much past 150 solar masses. R136A1 is 40 or 50 solar masses heavier than that. The math does not quite close. The second idea is stellar mergers. Maybe R136A1 did not form as a single star. Maybe it started as 2 or 3 smaller stars orbiting each other in a tight binary or triple system. Over time, the stars spiraled inward, eventually colliding and merging into a single object. Mergers are messy. They dump enormous amounts of energy into the surrounding gas. They mix the interiors of both stars, bringing fresh hydrogen up from the core and extending the lifetime of the merged object. And they can, in principle, produce stars heavier than the Eddington limit, because the limit applies to stars forming from gas, not to stars assembling from pre-existing stellar material. If you smash two 70 solar mass stars together, you get a 140 solar mass star. Smash a third one into that and you are at 210. Keep going and you can build something like R136A1. The problem with the merger scenario is that it predicts the star should be rotating extremely fast. When two stars merge, they dump their orbital angular momentum into the final object. The result should be a star spinning at hundreds of kilometers per second at the equator, possibly fast enough to fling material off into space. R136A1 is rotating, but not that fast. Observations suggest it is spinning at around 300 kilometers per second, which is quick but not outrageous for a star of its type. If it formed from a merger, something must have carried away most of the angular momentum. Maybe a disk of gas around the star, maybe a strong stellar wind, maybe another companion star that has since wandered off. All of those are possible, but none of them are certain. The third idea is the most uncomfortable. Maybe the physics is wrong. Maybe the Eddington limit, as it is currently understood, does not apply in all environments. Maybe there is something about the conditions in the R136 cluster, the density, the composition, the radiation field, that allows stars to grow heavier than the standard models predict. If that is the case, then R136A1 is not an outlier, it is a clue, a signal that the equations governing star formation need another term, another correction factor, another layer of complexity that no one has thought to include yet. This is the option no physicist wants to pick, because it opens the door to the possibility that other assumptions are wrong too. But it is on the table. The star is not alone. The R136 cluster contains at least 9 other stars heavier than 100 solar masses. R136A2 weighs around 195 solar masses. R136A3 is about 150. The cluster is full of monsters. That concentration is what makes the whole thing so strange. If massive stars this heavy are supposed to be rare, why are there 10 of them sitting in the same room? If the conditions needed to form them are supposed to be unusual, why did those conditions apparently occur over and over again in the same small patch of space? One possibility is that the cluster itself is unusual. The Tarantula Nebula is one of the most violent star-forming regions within a few million light-years of Earth. It is pumping out new stars at a rate of about 1 solar mass per year, which does not sound like much until you realize that the Milky Way as a whole only forms about 2 or 3 solar masses worth of stars per year. The Tarantula Nebula, a region only a few hundred light-years across, is producing half as many stars as an entire galaxy. That kind of activity creates feedback loops. Massive stars form, ignite, and start blowing powerful winds into the surrounding gas. Those winds compress nearby clouds, triggering more star formation. The new stars form faster and heavier because the gas is already compressed. The process feeds on itself. In a runaway environment like that, the normal rules might not apply. Stars might be able to grow heavier than they could in a quieter region of space. Another possibility is that the R136 cluster is younger than we think. Current estimates place its age at around 1 to 2 million years. That is young even by stellar standards. Massive stars live fast. A 200 solar mass star burns through its fuel in only a few million years before going supernova. If the cluster is closer to 1 million years old rather than 2, then all of the massive stars in it formed essentially at the same time, in the same burst of activity. That would explain the concentration. It would also mean that within the next few million years, the entire cluster is going to start detonating. One supernova after another, possibly triggering more star formation in the surrounding gas, possibly blowing the whole region apart. The Large Magellanic Cloud is going to have a very interesting few million years. R136A1 itself is not going to last much longer. At its current mass loss rate, it is shedding about 1 solar mass every 30,000 years. That might sound slow, but the star is only a few million years old, and it only weighs about 200 solar masses. Do the math and you realize the star has already lost a significant fraction of its birth mass. It might have started at 250 or 300 solar masses and blown off the outer layers over time. If that is the case, then the star we are looking at now is not the star that formed. It is what is left after millions of years of shedding material into space. A Wolf-Rayet star in the making. Wolf-Rayet stars are a class of massive stars that have lost most or all of their outer hydrogen layers. What you are looking at when you see a Wolf-Rayet star is essentially the exposed core of a supergiant. The outer envelope has been blown away by stellar winds, leaving behind a core that is fusing heavier elements, helium into carbon, carbon into oxygen, oxygen into neon. The surface temperature of a Wolf-Rayet star can reach 50,000 degrees Celsius or more. The winds are so strong that they blow off material at speeds of thousands of kilometers per second. The star is eating itself from the outside in, racing toward a supernova that is now inevitable. R136A1 has not reached that stage yet, but it is getting close. Its spectrum shows strong emission lines from ionized helium and nitrogen, which is a sign that the outer hydrogen layers are already heavily depleted. The star is transitioning. In a few 100,000 years, maybe less, it will cross the line into Wolf-Rayet territory, and a few 100,000 years after that, it will explode. The explosion will be visible across the local group. If it happens in the next few 100,000 years, and if anyone on Earth is still pointing telescopes at the Large Magellanic Cloud when it does, we will see a supernova bright enough to cast shadows at night. The energy released will be equivalent to the Sun's entire lifetime output compressed into a few weeks. The core will collapse into a black hole weighing 50 or 60 solar masses. The outer layers will be hurled outward at a significant fraction of the speed of light, slamming into the surrounding gas and lighting up the Tarantula Nebula like a flashbulb. The shockwave will compress nearby clouds, triggering another round of star formation, and the cycle will continue. That is the fate of every star in the R136 cluster. They are all on the clock. They are all burning through their fuel at rates that would bankrupt a smaller star in a geological eye blink. And they are all going to die violently. The cluster is a preview of what the universe looked like in its earliest days, when star formation was more chaotic, when gas clouds were denser and less polluted by heavy elements, when the first generation of massive stars ignited and began the process of enriching the cosmos with carbon, oxygen, and iron. The conditions that allowed R136A1 to form are not common now, but they were common once. And if we want to understand how the universe went from a cloud of hydrogen and helium to a place where planets and people can exist, we need to understand how stars like this are born. The Eddington limit is still real. Radiation pressure still fights gravity. Stars still have a maximum mass, but the maximum is not as hard as we thought. It can be pushed, it can be bent under the right circumstances, and in rare environments like the R136 cluster, it can be exceeded, not by a little, by a lot. R136A1 is not an impossible star, it is an improbable star. And the fact that it exists tells us that improbable things happen more often than the equations suggest they should. The universe is not tidy, it does not round numbers. It does not care that a star weighs 40 solar masses more than the textbook says it is allowed to. It builds the star anyway and leaves us to figure out how. The answer is still not clear. Maybe it is mergers, maybe it is runaway accretion, maybe it is physics we have not worked out yet. What is clear is that the largest stars by mass are not the largest stars by size. R136A1 weighs 200 times more than the Sun, but it is only about 30 times wider. It is dense, hot, and compact. The stars we are building toward, the ones that will swallow planets if you drop them into our solar system, are a different beast entirely. They are not the heaviest, they are the most swollen. They are dying, and their deaths are slow, messy, and spectacular. That is where we are going next, to the stars that have run out of time and started tearing themselves apart from the inside out. The stars that have run out of time do not go quietly, they do not fade, they do not dim into the background like a candle burning down to its wick. They scream, they hurl their own guts into space at speeds that would liquefy anything in their path. They shed mass the way a human sheds skin, except instead of dead cells, they are throwing off layers of ionized gas weighing more than entire planets. And they do this for thousands of years, burning hotter and brighter with every passing century, until the core finally runs out of things to fuse and the whole structure collapses in on itself in less time than it takes you to blink. These are the Wolf-Rayet stars, and they represent one of the most violent phases any massive star can pass through before it dies. The name comes from two French astronomers, Charles Wolf and Georges Rayet, who in 1867 were studying stars in the constellation Cygnus using a new tool called a spectroscope. A spectroscope splits starlight into its component colors, revealing the chemical fingerprints of whatever is producing that light. Most stars showed dark lines in their spectra, absorption lines where specific elements in the star's atmosphere had absorbed light at particular wavelengths. Wolf and Rayet found 3 stars that had something different. Instead of dark lines, they had bright emission lines. The stars were not just passively glowing, they were actively radiating energy at specific wavelengths, like neon signs flickering in the dark. The emission lines were broad, smeared out across a range of wavelengths, which meant whatever was producing them was moving fast, very fast, hundreds or thousands of kilometers per second fast. Nobody understood what they were looking at. The stars did not fit into any known category. They were too hot, too bright, too strange. It took decades to work out what was actually happening, and the answer, when it finally came together, was unsettling. These were not normal stars, they were the exposed cores of dying supergiants, stripped of their outer hydrogen layers and blowing themselves apart from the inside out. A Wolf-Rayet star begins its life the same way every massive star does. A cloud of gas collapses under its own gravity. The center heats up. Nuclear fusion ignites. Hydrogen fuses into helium, releasing energy that holds the star up against its own weight. For a star with 20 or 30 or 50 times the mass of the Sun, this phase lasts a few million years, not long by cosmic standards, but stable, predictable. The star sits on the main sequence, burning steadily, and from the outside it looks like it could go on forever. Then the hydrogen in the core runs out. The fusion reactions slow down. The core starts to contract under its own weight. As it contracts, it heats up. Eventually it gets hot enough to start fusing helium into carbon. That releases energy again, which pushes the outer layers of the star outward. The star swells. It becomes a supergiant. The surface cools, turning red, but the sheer size of the star makes it incredibly luminous. A red supergiant can outshine the Sun by a factor of 10,000 or more, even though its surface is only half as hot. That phase does not last long either. A star like Betelgeuse, currently one of the most famous red supergiants in the sky, will spend maybe a few 100,000 years in that state before moving on to the next stage. And the next stage, for the most massive stars, is where things get messy. The helium in the core eventually runs out. The core contracts again. It heats up again. It starts fusing carbon into oxygen, then oxygen into neon, then neon into magnesium, then magnesium into silicon. Each stage releases less energy than the one before. Each stage burns faster. The star is running through its fuel in a panic, fusing heavier and heavier elements in a desperate attempt to keep the core hot enough to resist gravity. But it is a losing battle. Every fusion reaction is less efficient than the last, and the outer layers of the star, still bloated from the earlier red supergiant phase, are so loosely bound that the star's own light is beginning to push them away. This is where the Wolf-Rayet phase begins. The star develops a stellar wind, a continuous stream of gas blowing off the surface and into space. Stellar winds are common. The Sun has one. A thin trickle of charged particles flows outward from the Sun's surface at all times, carrying away a tiny fraction of the Sun's mass. Over the Sun's entire lifetime, it will lose maybe 1/10,000th of its total mass to its wind, not enough to matter. The wind from a Wolf-Rayet star is not a trickle, it is a hurricane. The particles are not drifting outward. They are being hurled at speeds of up to 3,000 kilometers per second, roughly 1% of the speed of light, and the amount of material being blown away is staggering. A typical Wolf-Rayet star loses about 1/10,000,000th of a solar mass per year to its wind. That does not sound like much until you convert it into units that make sense. 1/10,000,000th of a solar mass is roughly 300 times the mass of Earth every year. That is an Earth every day and a quarter. The star is shedding planets' worth of material continuously, and it does this for tens or hundreds of thousands of years before it finally runs out of fuel and explodes. Where is all that material going? Into space. It forms a bubble around the star, a shell of ionized gas expanding outward at thousands of kilometers per second. That gas glows. It glows because the ultraviolet light from the star is slamming into it and stripping electrons off the atoms, a process called ionization. When those electrons recombine with the atoms, they release light at specific wavelengths. Those are the bright emission lines Wolf and Rayet saw in 1867. The lines are broad because the gas is moving so fast. Some of it is moving toward us, some of it is moving away, and the Doppler shift smears the wavelengths across a range. The faster the gas moves, the broader the lines. A Wolf-Rayet star with emission lines spread across dozens of angstroms is telling you that its wind is blowing at a significant fraction of the speed of light. The wind is driven by radiation pressure. Light carries momentum. When photons from the star's core work their way up through the outer layers and finally escape into space, they collide with atoms in the star's atmosphere and transfer some of their momentum. For a normal star, that pressure is negligible. For a Wolf-Rayet star, which is pumping out ultraviolet light at a rate tens of thousands or even hundreds of thousands of times greater than the Sun, the pressure is enormous. It is strong enough to lift the outer layers off the star entirely. Gravity is still pulling inward, trying to hold the star together, but radiation pressure is pushing outward harder. The result is a constant flow of material away from the surface. This process strips the star. Layer by layer, the hydrogen envelope gets blown away. Eventually, the helium layer underneath gets exposed. Then that gets blown away too. What you are left with, in the most extreme cases, is a bare stellar core sitting in the middle of a glowing nebula of its own discarded guts. The core is small, dense, and unimaginably hot. Surface temperatures can reach 50,000 degrees Celsius or more, 10 times hotter than the Sun. The core is fusing carbon, oxygen, or heavier elements depending on how far along the star is in its death spiral. And it is still losing mass. Even at this stage, the wind does not stop. The star is tearing itself apart all the way to the end. Astronomers classify Wolf-Rayet stars into subtypes based on which elements show up most prominently in their spectra. WN stars show strong nitrogen lines, which means they have lost their outer hydrogen layers but still have some helium left. WC stars show strong carbon and oxygen lines, which means they have lost the helium layer too and are now exposing the carbon-oxygen core. WO stars, the rarest subtype, show strong oxygen lines and represent the final stage before the star explodes. The progression from WN to WC to WO is essentially a countdown. Each subtype represents a deeper layer of the star being peeled away. By the time you get to WO, you are looking at a star that has maybe a few thousand years left before it detonates. Wolf-Rayet stars are rare. There are only a few hundred known in the Milky Way, compared to hundreds of billions of stars total. They are rare because the phase does not last long and because only the most massive stars ever reach it. A star has to start with at least 25 solar masses to have any chance of becoming a Wolf-Rayet star. Anything smaller will lose its outer layers more gradually, possibly through a planetary nebula phase, and end up as a white dwarf. Anything heavier will blast through the Wolf-Rayet phase in a few 100,000 years and then go supernova. You need to catch the star at exactly the right moment, and even when you do, they are often difficult to study because they are surrounded by so much glowing gas that it obscures the star itself. The winds from Wolf-Rayet stars are not just fast, they are dense. The gas being blown off is not a thin wisp. It is a thick, optically opaque shell that can completely hide the underlying star from view. Astronomers studying Wolf-Rayet stars are often not looking at the star itself. They are looking at the wind. The star is buried somewhere in the middle, invisible, detectable only through the ultraviolet light it is pumping into the surrounding gas. That makes measuring the star's properties difficult. You cannot directly see the surface. You cannot measure its radius. You have to infer everything from the spectrum of the wind and hope your models are accurate. One of the best studied Wolf-Rayet stars is WR104, also known as Gamma Velorum. It sits about 1,100 light-years from Earth in the constellation Vela, and it is one of the brightest Wolf-Rayet stars in the sky. Gamma Velorum is actually a binary system. The Wolf-Rayet star is orbiting a blue supergiant companion, and the two stars are close enough that their winds collide in the space between them, creating a shock front that glows in X-rays. Observations of Gamma Velorum have given astronomers a detailed look at how Wolf-Rayet winds behave. The wind from the Wolf-Rayet star is blowing at about 1,500 kilometers per second. It is losing about 1.5 times 10 to the negative 5 solar masses per year, which translates to roughly 5,000 Earth masses per year. The wind from the companion star is slower but still strong, blowing at about 400 kilometers per second. Where the two winds meet, the gas heats up to millions of degrees and radiates X-rays. The whole system is a laboratory for studying how massive stars interact and how their winds shape the space around them. The collision between the winds also creates structure. Instead of a smooth spherical bubble, the nebula around Gamma Velorum is full of arcs, filaments, and shock fronts, where faster-moving gas has caught up with slower-moving gas and piled up. Over time, those structures drift outward and fade, but new ones keep forming as long as the stars keep blowing winds. The result is a constantly changing, constantly evolving nebula that looks different every time you point a telescope at it. Wolf-Rayet stars are not just interesting because they are bright and violent, they are interesting because of what they leave behind. When a Wolf-Rayet star finally runs out of fuel and the core collapses, the result is a supernova. But not just any supernova. The outer layers of the star, the hydrogen and helium that would normally be present, have already been blown away. So when the explosion happens, there is no hydrogen in the ejected material. The spectrum of the supernova shows no hydrogen lines. Astronomers call these type Eb or type IC supernovae, depending on whether helium is present. Type E means the hydrogen is gone, but some helium remains. Type EC means both the hydrogen and the helium are gone. The star has been stripped all the way down to the core before it exploded. These stripped supernovae are important because they are one of the main ways the universe gets seeded with heavy elements. When a massive star explodes, it does not just scatter hydrogen and helium into space. It scatters carbon, oxygen, nitrogen, silicon, iron, and every other element up to and including uranium. Those elements were forged in the core of the star during the final stages of its life, and the explosion is what distributes them into the surrounding gas clouds. Future generations of stars form from those enriched clouds. Planets form from the dust and debris. Life, if it forms at all, is built from atoms that were created inside stars and blown into space by supernovae. Every carbon atom in your body, every oxygen atom in the air you breathe, every iron atom in your blood was manufactured inside a star and delivered to Earth by a supernova. Many of those atoms came from Wolf-Rayet stars. The explosion itself is almost incomprehensibly violent. The core of the star, now composed mostly of iron, collapses in less than a second. Iron is the end of the line for fusion. Fusing iron does not release energy, it absorbs energy. So once the core is made of iron, there is no more fuel, no more outward pressure, nothing to hold the core up. Gravity wins. The core collapses from roughly the size of Earth to the size of a city in about 1 second. The collapse happens so fast that the outer layers of the core do not have time to react. They are still falling inward when the core reaches nuclear density and rebounds. The rebound sends a shock wave racing outward through the star at a significant fraction of the speed of light. When the shock wave reaches the surface, the star explodes. The energy released in that explosion is roughly equal to the total energy the Sun will produce over its entire 10 billion year lifetime, except it all happens in a few weeks. The explosion leaves behind one of two things. If the core is heavy enough, it collapses into a black hole. If the core is lighter, It collapses into a neutron star, an object about 20 kilometers across, but weighing more than the Sun, held up not by normal atomic forces, but by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being packed any tighter. Neutron stars are the densest objects in the universe that are not black holes. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity at the surface is so strong that if you dropped an object from a height of 1 meter, it would hit the ground at several million kilometers per hour. Not all Wolf-Rayet stars explode the same way. Some are thought to be the progenitors of gamma-ray bursts, the most energetic explosions in the universe after the Big Bang itself. A gamma-ray burst occurs when a massive star collapses and the core forms a black hole. If the star is rotating rapidly, the infalling material forms a disk around the black hole, and jets of material are launched from the poles at nearly the speed of light. Those jets punch through the outer layers of the star and burst into space, releasing more energy in a few seconds than the Sun will release in its entire lifetime. If one of those jets happens to be pointed at Earth, we see a gamma-ray burst. If it is not, we see nothing. Gamma-ray bursts are rare, but Wolf-Rayet stars, with their rapid rotation and their stripped cores, are prime candidates. The winds from Wolf-Rayet stars also shape the regions around them. The gas being blown off does not just drift into space and disappear. It slams into the surrounding interstellar medium, the thin gas that fills the space between stars, and creates bubbles, shells, and cavities that can be hundreds of light years across. Those structures compress nearby gas clouds, triggering new rounds of star formation. In a very real sense, Wolf-Rayet stars are the gardeners of the galaxy. They plow the fields, enriching the soil with heavy elements, and prepare the ground for the next generation of stars and planets. Without them, the universe would still be mostly hydrogen and helium. There would be no carbon, no oxygen, no silicon, no iron, no rocky planets, no chemistry, no life. The most massive Wolf-Rayet stars shed so much mass that by the time they explode, they weigh significantly less than they did when they were born. A star that started at 60 solar masses might end its life at only 20 or 30 solar masses. The rest has been blown into space over the course of a few 100,000 years. That mass loss changes the star's fate. A 60 solar mass star would normally collapse into a black hole weighing 50 or 60 solar masses. But if it loses half its mass before it explodes, the black hole left behind might weigh only 10 or 15 solar masses. The mass loss also changes the dynamics of the explosion. A lighter star explodes more gently than a heavier star. The supernova is less energetic. The amount of heavy elements produced is smaller. The remnant is smaller. Everything downstream of the mass loss is affected. The transition from a normal massive star to a Wolf-Rayet star is not always gradual. In some cases, it happens suddenly. A star in the red supergiant phase can undergo an eruption, a brief period where it loses an enormous amount of mass in a short time. The most famous example of this is Eta Carinae, a star about 7,500 light-years from Earth, that in the 1840s underwent an eruption so violent that it became the second brightest star in the sky, outshining everything except Sirius. The eruption lasted about 20 years. During that time, the star lost somewhere between 10 and 40 solar masses. The ejected material formed 2 lobes of gas, now known as the homunculus nebula, that are still expanding outward today. Eta Carinae is not technically a Wolf-Rayet star yet, but it is on its way. It has lost most of its hydrogen envelope. Its surface temperature is climbing. Within a few thousand years, it will likely transition into a full-blown Wolf-Rayet star and begin the final countdown to supernova. The existence of Wolf-Rayet stars tells us something important about how the universe works. Stars are not static, they are not eternal. They are dynamic, evolving objects that change dramatically over their lifetimes. The most massive stars spend the vast majority of their lives as unremarkable main-sequence objects, burning hydrogen in their cores and sitting quietly on the Hertzsprung-Russell diagram. Then, in the last few 100,000 years of their lives, they transform, they swell into supergiants. They shed their outer layers, they expose their cores, they blow winds at a fraction of the speed of light. And then they explode, seeding the galaxy with the elements needed to build planets and people. The entire sequence, from birth to death, takes only a few million years. For a star like the Sun, which will live for 10 billion years, that is a blink. For a Wolf-Rayet star, it is an entire lifetime compressed into a geological instant. The Sun will never become a Wolf-Rayet star. It does not have enough mass. It will never fuse carbon or oxygen in its core. It will never develop a stellar wind strong enough to strip away its outer layers. It will never explode, but it will change. In about 5 billion years, the hydrogen in the Sun's core will run out, and the Sun will begin its own transformation. It will swell into a red giant, expanding until its outer layers drift past the orbit of Earth. It will shed those layers in a much gentler process than a Wolf-Rayet wind, forming a planetary nebula that will glow for a few tens of thousands of years before fading. And it will leave behind a white dwarf, a cooling ember about the size of Earth, slowly radiating away the last of its heat over trillions of years. That is the fate of an average star, quiet, gradual, almost boring compared to the pyrotechnics of a Wolf-Rayet star. But it is coming, and understanding what happens to the Sun, how it will swell and how it will shed its outer layers, is where we are going next. The stars that tear themselves apart in Wolf-Rayet winds are extreme. They are rare. They represent the end stage of the most massive stars in the universe, the ones that live fast and die violently. But they are not the only stars that swell. They are not the only stars that shed their outer layers and expose their cores to the universe. Every star, from the smallest red dwarf to the largest supergiant, has a life cycle. And for stars like our Sun, that life cycle includes a phase where the surface expands, the core contracts, and the entire structure transforms into something unrecognizable. The Sun is not going to explode. It is not going to blow off its outer layers in a stellar wind moving at thousands of kilometers per second. It is not going to leave behind a neutron star or a black hole, but it is going to change, and that change, when it comes, will be catastrophic for everything in the inner solar system. The Sun has been burning steadily for about 4.5 billion years. It formed from a collapsing cloud of gas and dust, left over from previous generations of stars that had lived, died, and scattered their guts into space. The cloud collapsed under its own gravity, the center heated up, nuclear fusion ignited, hydrogen atoms in the core started slamming together under immense pressure and heat, fusing into helium and releasing energy in the process. That energy pushed outward, holding the star up against the inward pull of gravity. The balance between those two forces, gravity pulling in and fusion pressure pushing out, is what keeps the Sun stable. It has been stable for billions of years. It will remain stable for billions more. Then the hydrogen in the core will run out and the balance will break. Stars do not burn the way fires burn. There is no oxygen, there is no combustion. The word burn is misleading, but it is the word we use because there is no better shorthand for what is happening. Fusion is not burning. It is a nuclear reaction where lighter elements are smashed together to form heavier ones. In the Sun's core, hydrogen nuclei, which are just single protons, collide with enough energy to overcome the electric repulsion between them. When they stick together, they form helium. 4 hydrogen nuclei eventually combine into one helium nucleus. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into it. The missing mass is converted into energy. That is what Einstein's equation tells you. Mass and energy are the same thing in different forms, and the conversion rate is absurdly high. A tiny amount of mass converts into an enormous amount of energy. The Sun converts about 600 million tons of hydrogen into helium every second. It has been doing that for 4.5 billion years, and it still has enough hydrogen left in the core to keep doing it for another 5 billion years, but not forever. Eventually, the hydrogen in the core will run out. Not all at once. Gradually, the fusion reactions will slow down. The core will produce less energy. The outward pressure will drop. And gravity, which has been waiting patiently this entire time, will start to win. The core will contract. As it contracts, it will heat up. Compress a gas and it gets hotter. That is basic thermodynamics. The core of the Sun, now composed mostly of helium, with a thin shell of hydrogen still burning around it, will contract and heat up until the temperature rises high enough to ignite the next stage of fusion, helium fusion. Helium nuclei smashing together to form carbon and oxygen. Before that happens, the star will change shape, the core contracts. The outer layers, no longer supported by the same level of outward pressure, start to expand. This sounds backward. The core shrinks and the surface grows, but it makes sense when you look at the energy flow. The contracting core heats up. The heat radiates outward through the layers above it. Those layers absorb the energy and puff up, like a balloon being inflated from the inside. The surface of the star moves outward, the radius increases, the surface area grows, and because the surface area is now so much larger, the same amount of energy gets spread out over a much bigger space. The surface cools, the star's color shifts from yellow to red, the Sun will become a red giant. This is not speculation, this is what stars do. Astronomers have observed thousands of red giants in the Milky Way. They know what the process looks like. They know how long it takes. They know how big the stars get. And they can run the models forward to predict what will happen to the Sun with a high degree of confidence. The Sun is not special. It is not exempt. It will follow the same path every other star of its mass has followed. The expansion will not happen overnight. It will take hundreds of millions of years. The Sun will swell gradually, increasing in radius by a few % every million years. For a long time, the change will be subtle. Then it will accelerate. The core will contract faster. The outer layers will expand faster. The Sun will bloat. Its radius will grow from about 700,000 kilometers, roughly 109 times the diameter of Earth, to something closer to 150 million kilometers. That is roughly 1 astronomical unit, 1 AU, the current distance from the Earth to the Sun. The Sun will expand until its outer layers reach the orbit of Earth, maybe beyond. Mercury will be the first to go. Mercury orbits at about 0.4 AU. When the Sun expands past that point, Mercury will find itself inside the Sun's outer envelope. The envelope is not solid. It is a thin gas, far less dense than the air you are breathing right now. But it is hot, thousands of degrees. Mercury will spiral inward, dragged by friction with the gas. It will heat up. The surface will melt. The entire planet will vaporize over the course of a few thousand years, dissolving into the Sun like a sugar cube in hot water. Venus will follow. Venus orbits at about 0.7 AU. Same process, same outcome. The planet will be engulfed, heated and destroyed. The thick atmosphere that currently makes Venus the hottest planet in the solar system will be stripped away in a matter of centuries. The rocky surface will liquefy. The entire planet will eventually be consumed. Earth is the question mark. Earth orbits at 1 AU. The Sun's expansion will bring its surface close to Earth's orbit, possibly past it. Whether Earth gets swallowed depends on a few factors that are difficult to predict with certainty. As the Sun swells, it will lose mass. The outer layers will drift away into space, shed gradually over millions of years. As the Sun loses mass, its gravitational pull on the planets will weaken. The planet's orbits will drift outward slightly. Earth might drift far enough to avoid being engulfed, or it might not. The math is tight. Current models suggest Earth has about a 50-50 chance of surviving the initial expansion. But survival is a relative term. Even if Earth avoids being consumed, it will not be habitable. Long before the Sun swells to 1 AU, Earth will be sterilized. The Sun's luminosity will increase. It is already increasing slowly as the core burns through its hydrogen and the fusion reactions gradually shift outward into the surrounding shell. Over the next billion years, the Sun will get about 10% brighter. That does not sound like much. It is enough to boil the oceans. Earth's temperature is finely balanced. A small increase in solar output pushes the climate past a tipping point. Water vapor, a greenhouse gas, traps more heat. More heat causes more evaporation. More water vapor traps more heat. The feedback loop runs away. Within a few 100 million years, Earth will resemble Venus, a runaway greenhouse. Surface temperatures well above the boiling point of water. No liquid water, no atmosphere capable of supporting life. Everything on the surface will be dead. That is the preview. The full transformation, the red giant phase, will come a few billion years later. By that time, Earth, if it still exists, will be a charred cinder orbiting a bloated red star. The Sun's surface temperature will have dropped to around 3,000 degrees Celsius. Cool by stellar standards, but still hot enough to glow a dull red. The Sun will be so large that if you could stand on its surface, which you could not because there is no solid surface, the horizon would curve away from you at a rate so gentle you would not notice. The Sun will fill half the sky, as seen from what is left of Earth's orbit. It will be close enough that you could see structure on its surface, if there were anyone left to look. Convection cells, each one larger than Jupiter, churning slowly through the outer layers, dark spots where cooler gas sinks, bright spots where hotter gas rises. The whole thing boiling like water in a pot. The core, meanwhile, will have reached the point where helium fusion can ignite. This does not happen smoothly. For a star like the Sun, the helium flash is sudden. The core has been contracting for hundreds of millions of years, heating up but not quite hot enough to fuse helium. Helium requires a higher temperature than hydrogen, about 100 million degrees Celsius compared to 15 million for hydrogen. The core finally hits that temperature and the helium starts fusing. But the core is in a strange state. It is degenerate. The pressure holding it up is not coming from heat, it is coming from quantum mechanics. Electrons, packed so tightly that they resist being compressed any further, provide the pressure. When the helium ignites in a degenerate core, the energy release does not increase the pressure the way it would in a normal gas. The core does not expand to regulate the fusion. Instead, the fusion runs out of control. The temperature spikes. More helium fuses. The temperature spikes higher. The reaction accelerates. For a few seconds, the core of the Sun produces as much energy as the entire Milky Way galaxy. Then the temperature gets high enough that the degeneracy breaks. The core expands, the pressure drops, the fusion stabilizes, the helium flash is over. You would not see any of this from the outside. The flash happens deep in the core, buried under layers of gas hundreds of thousands of kilometers thick. The outer layers do not have time to react. By the time the energy from the flash works its way to the surface, the core has already stabilized and the star has settled into a new equilibrium. The Sun will shrink slightly after the helium flash, contracting to maybe 50 or 60 times its current radius. Still a giant, but not quite as bloated. It will stay in that state for about 100 million years, fusing helium into carbon and oxygen in the core, while a shell of hydrogen continues to fuse in the layers above. Then the helium will run out, the core will contract again, the outer layers will expand again. The Sun will swell even larger than it did the first time. This is the asymptotic giant branch phase, and it is the final act before the Sun sheds its outer layers entirely and becomes a white dwarf. During the asymptotic giant branch phase, the Sun will undergo thermal pulses. Every few thousand years, the helium shell burning around the core will briefly flare up, dumping a huge amount of energy into the layers above. The star will brighten, the outer layers will puff up. The wind will strengthen. Each pulse strips away a little more of the envelope. The Sun will lose mass at a rate of about 1/10,000th of a solar mass per year, not as fast as a Wolf-Rayet wind, but steady. Over the course of a few 100,000 years, the Sun will shed most of its remaining envelope. The material will drift outward, forming a shell of gas around what is left of the core. The core, now exposed, will be incredibly hot, tens of thousands of degrees at the surface. The ultraviolet light from the core will ionize the surrounding gas. The gas will glow, forming a planetary nebula. Planetary nebulae have nothing to do with planets. The name comes from early telescopes that could not resolve the structures clearly. To an 1800s astronomer looking through a small telescope, a planetary nebula looked like a fuzzy disk, similar to the appearance of a planet. The name stuck even after better instruments revealed that these were expanding shells of gas surrounding dying stars. The planetary nebula will last for about 10,000 years, then it will fade as the gas spreads out and cools. What remains will be the core, a white dwarf, an object about the size of Earth, weighing about half the mass of the Sun, supported not by fusion but by electron degeneracy pressure. The same quantum effect that held up the Sun's core during the helium flash will now hold up the entire star. The white dwarf will not be generating energy. It will just be radiating away the heat left over from the fusion reactions that stopped millions of years earlier. It will glow white hot at first, with a surface temperature of around 100,000 degrees Celsius. Then it will cool. Over billions of years, trillions of years, it will fade through white, yellow, red, and eventually black, a black dwarf, a cold, dark cinder drifting through space. That is the end of the Sun. No explosion, no supernova, just a slow, quiet fade. The planetary nebula will be visible from anywhere in the galaxy, assuming there is anyone left to see it. It will glow in visible light, ultraviolet and infrared. It will be a marker, a tombstone, announcing that a star has died. The gas in the nebula will carry with it all the carbon, oxygen, nitrogen, and other elements that were forged in the Sun's core over billions of years. That gas will drift into space, mix with the interstellar medium, and eventually collapse into new clouds that will form new stars and new planets. The atoms that once made up the Sun, and the atoms that once made up Earth, if any of them survive, will be recycled. The universe does not waste material. Every atom gets reused. The Sun's death will be the beginning of something else. This entire sequence, from the moment the core hydrogen runs out, to the final white dwarf fade will take about 7 or 8 billion years. Add that to the current age of the Sun, and you get a total lifespan of about 12 billion years. The Sun is not old, it is middle-aged. It has spent 4.5 billion years on the main sequence, and it has another 5 billion to go before it leaves. But the clock is ticking, and the changes that will occur are not gradual in the sense that you could watch them from day to day. They are gradual on a geological timescale. On a human timescale, the Sun will appear to be stable and unchanging for the entirety of human history and far beyond. But on a cosmic timescale, the Sun's transformation into a red giant is already written. The script is set, the physics is understood, and there is nothing anyone can do to stop it. Comparing the Sun's future to the extreme red giants like Scuti is instructive because it shows that the process is the same even if the scale is different. Scuti is not a different kind of object. It is a star that started with more mass than the Sun and went through the same red giant phase, just faster and more dramatically. The Sun will expand to maybe 100 times its current radius. Scuti expanded to more than 1,000 times its original radius. The Sun will fuse helium in its core for 100 million years. Scuti burned through its fuel in a few million years. The Sun will shed its outer layers gently, forming a planetary nebula. Scuti is shedding its layers now, blowing off mass in a thick wind that surrounds the star like fog. The physics is identical, the numbers are different, and those numbers matter because they determine what happens to the planets. A star like Scuti, if it had planets, would have destroyed them billions of years ago. The expansion would have been so extreme that anything within a few astronomical units of the star would have been vaporized. A star like the Sun will only destroy the inner planets. The outer planets, Jupiter, Saturn, Uranus, Neptune, will survive. Their orbits will drift outward as the Sun loses mass. They will be bathed in more intense radiation. Jupiter's icy moons might even melt briefly as the Sun's luminosity spikes during the red giant phase, but the planets themselves will remain intact. They are too far out to be engulfed. They are too massive to be blown away by the solar wind. They will orbit the white dwarf for trillions of years, cold and dark, frozen monuments to a solar system that once supported life. The inevitability of the Sun's transformation is uncomfortable. We do not like thinking about the end of the world on timescales longer than a human lifetime. It is too abstract, too distant. The Sun's red giant phase is billions of years away. Humanity might not exist by then. We might have left the solar system. We might have spread across the galaxy. Or we might be extinct, wiped out by something far more immediate than the slow death of the Sun. But the fact remains that the Sun will die, and when it does, it will take the inner solar system with it. That is the cost of living around a star. Stars are not eternal. They are temporary structures held up by a delicate balance between forces that will eventually tip. The Sun has been stable for 4.5 billion years. It will remain stable for another 5 billion. And then it will transform into something unrecognizable. The red giant phase is not unique to the Sun. It is the fate of every star between about 0.5 and 8 solar masses. Stars lighter than that never get hot enough to fuse helium. They stay on the main sequence for trillions of years and eventually fade into white dwarfs without ever swelling into giants. Stars heavier than 8 solar masses skip the red giant phase entirely and go straight to supergiant, then Wolf-Rayet, then supernova. The Sun sits in the middle. Average mass, average temperature, average lifespan, and a predictable, well-understood death. That predictability is both reassuring and chilling. We know what is coming. We can model it. We can calculate when it will happen and what the effects will be. but we cannot stop it. The universe does not care about our plans. It does not care about our civilizations or our hopes or our fears. It runs on physics, and physics says the sun will die. Understanding the sun's future is important not because we need to prepare for it, but because it gives us context for everything else. The sun is the baseline. It is the reference point. When astronomers talk about red giants or supergiants or hypergiants, they are talking about stars that have gone through the same process the sun will go through, just on different scales and with different outcomes. The sun will never become a supergiant. It will never blow a Wolf-Rayet wind. It will never explode, but it will swell. It will shed its outer layers. It will leave behind a remnant. And that process, that transformation from a stable main sequence star into a bloated giant and finally into a cooling ember, is the thread that connects the sun to the largest stars in the universe. Scuti started as a star much more massive than the sun. It burned through its hydrogen in a few million years instead of 10 billion. It swelled into a red supergiant instead of a red giant. Its radius expanded to more than 900 times the sun's radius, maybe more depending on which measurement you trust. If you placed Scuti where the sun is now, its surface would extend past the orbit of Jupiter, past Saturn, past Uranus, possibly past Neptune. The entire inner solar system would be inside the star. That is the scale we are building toward. Stars so large that they swallow solar systems. Stars so bloated that their surfaces are barely held together by gravity. Stars that represent the absolute extreme of what stellar evolution can produce. The sun's red giant phase is a preview, a scaled-down version of what happens when the process runs wild. And Scuti is the poster child for what happens when a star decides that merely being giant is not enough. There is a star sitting 5,900 light-years from Earth that has become the poster child for everything extreme in stellar astronomy. Its name is Scuti, and for a time it held the title of largest known star in the universe. That title has been challenged, revised and debated ever since, but the object itself remains one of the most staggering examples of what happens when a star decides that merely being a red giant is not enough. Scuti is a red supergiant, possibly a hypergiant, depending on which astronomer you ask. And it is so large that if you placed it where the sun currently sits, its surface would drift past the orbit of Jupiter. Not close to Jupiter, past Jupiter. The entire inner solar system, every planet you learnt about in school, would be inside the star. The numbers are difficult to process. Best current estimates place Scuti's radius at about 909 solar radii. That means you could line up 909 suns in a row from the center of Scuti to its surface. Some measurements push that number higher, closer to 1,500 or even 2,000 solar radii, depending on the method used and the assumptions baked into the analysis. The uncertainty is not a sign of bad science. It is a sign of how difficult these objects are to measure. Scuti is not sitting still. It is pulsating. Its surface is moving in and out over periods of months or years. The outer layers are so diffuse that defining where the star ends and space begins is more art than science. And the whole thing is surrounded by a thick shell of dust and gas that obscures the star itself, making direct observations almost impossible. So when you read that Scuti is 909 solar radii, what you are really reading is the best estimate one team could make using one set of data at one point in time. Another team with different data might get a different answer. But even at the lower end of the estimates, the scale is absurd. 909 solar radii translates to a radius of about 1.18 billion kilometers. Double that for the diameter, and you get 2.4 billion kilometers from one side of the star to the other. For context, the distance from the Sun to Earth is about 150 million kilometers. The distance from the Sun to Jupiter is about 780 million kilometers. Scuti's diameter is more than 3 times the distance from the Sun to Jupiter. If you wanted to drive across Scuti at highway speeds, 60 miles per hour, it would take you about 2.7 million years. If you could walk across it at 3 miles per hour, it would take you 54 million years. These are not useful comparisons because no one is walking across a star, but they illustrate how far outside the human scale this object is. There is no intuitive handle to grab onto. The numbers are too big. The only way to understand them is to stack comparison on top of comparison until something clicks. Here is another one. Light, the fastest thing in the universe, travels at about 300,000 kilometers per second. At that speed, light can circle the Earth 7.5 times in 1 second. It takes light about 8 minutes to travel from the Sun to Earth. It takes light about 43 minutes to reach Jupiter. Light from the Sun, if it kept going, would take about 5.5 hours to reach the outer edge of the solar system at Pluto's orbit. Now imagine a beam of light trying to travel around the circumference of Scuti, not through the diameter, around the edge. The circumference of a circle is a little over 3 times the diameter, so the circumference of Scuti is somewhere around 7.5 billion kilometers. Light would take about 7 hours to complete that trip. 7 hours for light, traveling at 300,000 kilometers per second. That is how big this star is. It is so large that light itself, which crosses interplanetary distances in minutes, needs more than 7 hours to go around it. You could watch the sun rise on one side of Scuti, wait all day, watch the sun set, go to sleep, wake up the next morning, and light from the opposite side of the star still would not have reached you yet. Scuti was first identified in 1860 during a survey conducted at the Bonn Observatory in Germany. At the time, it was just another faint star in a catalogue, logged under the designation BD-125055. Nobody realized what they were looking at. The star is sitting in the constellation Scutum, a small and relatively obscure constellation in the southern sky that most people have never heard of. Scutum is not one of the zodiac constellations. It does not have any bright stars. It does not form a recognizable shape. It is just a dim patch of sky that happens to sit near the plane of the Milky Way, which makes it rich in faint stars and dense star fields. Scuti blends into that background. Even though it is one of the largest stars in the galaxy, it is not visible to the naked eye. Its apparent brightness from Earth fluctuates between magnitude 8.29 and 10.56, depending on where it is in its pulsation cycle. For reference, the faintest stars you can see with your naked eye under perfect dark sky conditions are around magnitude 6. Scuti is dimmer than that. You need a telescope to see it at all, and even through a telescope, it looks like a faint reddish dot. Nothing about its appearance suggests that you are looking at an object large enough to swallow solar systems. The realization that Scuti was unusual came much later, after astronomers developed the tools to measure stellar temperatures and distances with precision. By analyzing the star's spectrum, they could determine its surface temperature. Scuti glows at about 3,500 degrees Kelvin, give or take. Some sources give slightly different numbers, around 3,365 Kelvin, but they are all in the same ballpark. For comparison, the Sun's surface temperature is about 5,700 Kelvin. Scuti is cooler. That is why it glows red instead of yellow. Cooler stars emit more of their light in the red and infrared parts of the spectrum. Hotter stars emit more in the blue and ultraviolet. The color of a star tells you its temperature, and the temperature tells you what stage of life the star is in. A red supergiant is not a young star. It is a dying star. It has burned through the hydrogen in its core, moved on to fusing heavier elements, and puffed up its outer layers to an extreme size in the process. But the surface temperature alone does not tell you how bright the star is. Brightness depends on both temperature and size. A star can be cool and still be incredibly luminous if it is large enough. Scuti is a perfect example. Its surface temperature is only about 60% of the Sun's, but its surface area is roughly 750 million times larger. 750 million. That is not a typo. The surface area of a sphere scales with the square of the radius. If you increase the radius by a factor of 900, you increase the surface area by a factor of 900 squared, which is about 810,000. And if you increase the radius by a factor of 1700, which some estimates suggest, the surface area goes up by a factor of nearly 3 million. Even at the lower estimates, Scuti has so much surface area that despite being cooler than the Sun, it pumps out vastly more total energy. Current estimates place its luminosity at about 124,000 times the Sun's luminosity. Some older estimates pushed that number much higher, into the hundreds of thousands or even 500,000, but more recent measurements with better data suggest the lower figure is more accurate. 124,000 times the Sun's luminosity is still staggering. The Sun produces about 3.8 times 10 to the 26th watts of power. Multiply that by 124,000, and you get a number with more than 30 digits. Scuti is producing more energy every second than the Sun will produce in several weeks, and it is doing this while shedding mass. The outer layers of Scuti are so loosely bound that the star is constantly losing material to space. Not as violently as a Wolf-Rayet wind, but steadily. The mass loss rate is probably around 1/10,000,000th of a solar mass per year, maybe more. That adds up over time. Scuti is surrounded by a shell of gas and dust that it has blown off over the last few 100,000 years. That shell obscures the star itself and makes precise measurements difficult. When astronomers point a telescope at Scuti, they are not seeing the star's surface directly. They are seeing the glow from the surrounding dust, heated by the star's radiation. The actual surface of the star is buried underneath, hidden from view. This is why the size measurements are so uncertain. You cannot just point a telescope at Scuti and measure its angular diameter. The star does not have a sharp edge. The outer layers fade gradually into the surrounding dust shell. Different wavelengths of light come from different layers. Measure the star in visible light and you get one radius. Measure it in infrared and you get a different radius. Measure it in radio waves and you get yet another radius. All of those measurements are correct in the sense that they are accurately recording what the instruments are seeing, but they are measuring different things. The visible light is coming from the photosphere, the layer where the gas becomes opaque. The infrared light is coming from the dust shell farther out. The radio waves are tracing the ionized gas even farther out. So which one is the true size of the star? The answer depends on what you mean by size. Astronomers generally use the photosphere as the definition of the star's surface, but even that is fuzzy for an object like Scuti. The mass of Scuti is another surprise. You would think a star this large would be incredibly heavy. It is not. Current estimates place the mass somewhere between 7 and 10 solar masses. Some sources go as low as 7, others go as high as 10. Either way, the mass is far lower than the size would suggest. For comparison, R136A1, the most massive star we have confirmed, weighs about 200 solar masses, but is only about 30 times the radius of the Sun. Scuti weighs a 20th as much, but is 30 times wider. The reason for the discrepancy is density. Scuti is not dense. The outer layers are so diffuse that the density is lower than the best vacuum ever created in a laboratory on Earth. You could fly a spaceship through the outer envelope of Scuti and not notice you were inside a star until the temperature started climbing. The gas is spread so thin that there is essentially nothing there by terrestrial standards. The entire star, despite its enormous volume, weighs only about 10 times as much as the Sun, because most of that volume is empty space with a few atoms drifting through it. The low mass tells us something important about Scuti's history. This star did not start with 10 solar masses. It started with much more, probably 20 or 25 or 30 solar masses. Over the course of a few million years, it burned through its hydrogen, swelled into a red supergiant, and began shedding mass through a stellar wind. By now, it has lost more than half, maybe 2/3, of its original mass. The material that used to be part of the star is now drifting through space, forming a nebula that will eventually mix with the interstellar medium and be recycled into future generations of stars. Scuti is not just large, it is actively dismantling itself. The star you see today is not the star that formed. It is what is left after millions of years of mass loss. This process of swelling and shedding is not unique to Scuti. It is what all massive stars do at the end of their lives. But Scuti is extreme even by the standards of red supergiants. Most red supergiants swell to a few hundred solar radii. Scuti has swollen to 900 or more. Why? The answer probably has to do with its mass, its composition, and the specifics of its internal structure. Stars with slightly different masses or slightly different amounts of heavy elements in their atmospheres can evolve along slightly different paths. Scuti seems to have hit a sweet spot where the conditions were just right to produce an object of truly extreme size. It is not the most massive red supergiant. It is not the most luminous, but it is, as far as we know, one of the largest. Visualizing Scuti in our solar system is the easiest way to grasp the scale. Imagine removing the Sun from the center of the solar system and dropping Scuti in its place. The surface of Scuti would extend outward in all directions from the center. Mercury, the closest planet to the Sun, orbits at about 58 million kilometers. Mercury would be deep inside Scuti, buried under hundreds of millions of kilometers of hot gas. Venus, at 108 million kilometers, would also be inside. Earth, at 150 million kilometers, would be inside. Mars, at 228 million kilometers, would be inside. The asteroid belt, sitting between Mars and Jupiter at distances ranging from 300 to 500 million kilometers, would be inside. Jupiter, the largest planet in the solar system, orbits at about 780 million kilometers. Scuti's radius at 1.18 billion kilometers would reach past Jupiter. The surface of the star would drift somewhere between Jupiter and Saturn, depending on which size estimate you use. Saturn orbits at about 1.4 billion kilometers. If Scuti is at the upper end of the size estimates, its surface would be close to Saturn's orbit. If it is at the lower end, it would stop short, but not by much. Now imagine what that would look like from Earth's perspective. If Earth somehow survived being inside the star, you would not see a sun, you would not see a distant glowing ball in the sky. You would be inside the star. The sky would glow a dull red in every direction. There would be no day or night because the light would be coming from all around you. The temperature would climb steadily as you moved deeper into the envelope, from a few thousand degrees near the edge to tens of thousands of degrees closer to the core. Nothing on Earth would survive. The oceans would boil away in seconds, the atmosphere would be stripped off. The rocky surface would melt and then vaporize. The entire planet would dissolve into the star like a grain of salt in an ocean. And this would happen to every inner planet. Mercury, Venus, Earth, Mars, the asteroid belt, all of it consumed. Jupiter might survive if it stayed outside the photosphere, but it would be bathed in intense radiation and heat. Its atmosphere would be blasted by winds from the star. The Galilean moons would be scorched. The planet would be transformed into something unrecognizable. The fact that a star can swell this large and still hold itself together is a testament to how weak gravity becomes when mass is spread over such an enormous volume. The escape velocity at the surface of Scuti is only a few kilometers per second, far lower than the escape velocity at the Sun's surface. If you were standing on a solid platform at the photosphere of Scuti, which you could not because there is no solid surface and you would be vaporized, you could throw a baseball hard enough that it would leave the star entirely. The gravitational pull is that weak. The only thing holding the star together is the fact that the gas does not have anywhere else to go. It is bound to the core, not by a strong gravitational grip, but by the sheer inertia of having been part of the star for millions of years. The gas is drifting outward slowly, pushed by radiation pressure and thermal expansion, but it has not accelerated to escape velocity yet. Eventually it will. The star is losing mass. The envelope is thinning. In a few 100,000 years, maybe less, Scuti will shed so much of its outer layers that what remains will no longer be a red supergiant. It will be a smaller, hotter object, possibly a Wolf-Rayet star, racing toward a supernova. Scuti is classified as a pulsating variable star. Its brightness changes over time as the star expands and contracts. The pulsations are not regular. They are semi-regular, meaning there is a pattern, but it is not perfectly consistent. The star brightens and dims over periods of months, with the brightness varying by about a factor of 4 from peak to trough. The pulsations are driven by instabilities in the star's outer layers. As the layers heat up, they expand. As they expand, they cool. As they cool, they contract. As they contract, they heat up again. The cycle repeats. For a star as large as Scuti, the pulsations are slow and deep. The entire envelope is oscillating, moving in and out by distances that could be tens of millions of kilometers. If you were watching Scuti from a nearby star system, you would see it swell and shrink over the course of months, its brightness flickering as the surface area changes. The discovery of Scuti's extreme size came relatively recently. For more than a century after it was first catalogued, nobody paid much attention to it. It was just another faint red star in a crowded field. Then, in the 1990s and 2000s, advances in infrared astronomy and interferometry allowed astronomers to measure the angular sizes of distant stars with unprecedented precision. Scuti was one of the targets. The measurements revealed that the star was not just large, it was enormous, larger than almost anything else that had been measured. For a time, it was crowned the largest known star in the universe, and that title made headlines. Science communicators latched onto it. YouTube videos were made, articles were written, Scuti became famous. Then the title started slipping. Other stars were measured. Some of them turned out to be larger. Some of the original measurements were revised. The uncertainty in the data became more apparent. It turns out that calling something the largest star in the universe is harder than it sounds because the measurements are difficult. The stars are variable, and the definition of size is not as clear-cut as you might think. Scuti is still one of the largest known stars. It is still in the conversation, but it is no longer the undisputed champion. Stars like Stephenson 2-18 and WOH G64 have entered the discussion, and depending on which measurements you trust, they might be larger. The title of largest star is not settled. It might never be settled. Every few years, new data comes in and the rankings shuffle. But the uncertainty does not diminish what WOH Scuti represents. This is a star that has pushed stellar evolution to its absolute limits. It has swollen to a size that seems impossible. It has maintained that size for thousands of years despite losing mass constantly. It has become a laboratory for studying the extremes of what stars can do. And it sits out there in the constellation Scutum, invisible to the naked eye, pulsing and glowing and shedding material into space, oblivious to the fact that a species of primates on a small rocky planet 5,900 light-years away has been staring at it through telescopes and trying to figure out how something that large can exist. If WOH Scuti were closer, it would dominate the sky. If it were sitting at the distance of Alpha Centauri, the nearest star system to the Sun at about 4 light-years away, it would appear as a massive red disk, far larger than the full moon, glowing dully enough that you could look at it directly without hurting your eyes. It would cast a faint red light across the Earth at night. It would be impossible to ignore, but WOH Scuti is not close. It is almost 6,000 light-years away. At that distance, its enormous size shrinks to a tiny point of light that you need a telescope to see. The light reaching us now left the star around 4000 BC, when humans were just beginning to develop writing, when the pyramids had not been built yet, when the entire recorded history of civilization was still in the future. That light has been traveling through space ever since, crossing the galaxy at the speed of light, and it is only now arriving at Earth. By the time we see it, the star has already changed. It might have swollen further, it might have shrunk, it might have already exploded. We have no way of knowing. The light takes 6,000 years to reach us, and there is no faster way to get information. We are looking at the past, and the past is telling us that 6,000 years ago, there was a star in Scutum that was almost incomprehensibly large. WOH Scuti will not last. Stars this large never do. The core is fusing heavier and heavier elements, working its way up the periodic table toward iron. Once the core fills with iron, fusion stops. There is no more fuel. The core collapses. The star explodes. WOH Scuti will become a supernova, probably within the next million years, possibly sooner. When it does, it will briefly outshine every other star in the galaxy. The explosion will be visible from Earth even in broad daylight, a new star appearing in the sky where none was before. It will fade over the course of weeks or months, leaving behind a neutron star or possibly a black hole, and a rapidly expanding shell of gas enriched with carbon, oxygen, and heavier elements. That gas will drift through space, eventually mixing with the interstellar medium and forming new clouds that will collapse into new stars. The atoms that were part of WOH Scuti will be recycled, scattered across the galaxy, incorporated into planets and moons and possibly life forms that have not been born yet. The universe does not waste material. Every atom gets reused, but WOH Scuti is not the only monster out there. It is not even the only contender for the title of largest star. There are other red supergiants, other hypergiants, other objects sitting at the edge of what stellar physics allows, and one of them, sitting in a neighboring galaxy, surrounded by so much dust that it took decades to measure properly, might be even larger. Its name is WOH G64, and it has been quietly sitting in the Large Magellanic Cloud, waiting for someone to notice just how extreme it really is. Scuti sits in our own galaxy, the Milky Way, roughly 6,000 light-years away. For all its size, for all its extreme luminosity, for all the ways it pushes the boundaries of what a star can be, it is still close enough that we can study it with relative ease. We can point ground-based telescopes at it. We can measure its spectrum. We can track its pulsations. We can watch it change over time. But there is another star, sitting in a neighboring galaxy, that has spent decades hiding behind a veil of dust and gas, so thick that for a long time nobody could tell how large it actually was. That star is WOH G64, and it might be even more extreme than Scuti. WOH G64 sits in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way at a distance of about 160,000 to 163,000 light-years from Earth. The Large Magellanic Cloud is not a distant speck. It is close enough to be visible to the naked eye from the southern hemisphere, where it appears as a faint smudge of light hanging in the sky like a detached piece of the Milky Way. Early explorers sailing south of the equator noticed it centuries ago and named it after Ferdinand Magellan, even though people living in the southern hemisphere had been staring at it for tens of thousands of years before any European ships showed up. The galaxy is small by galactic standards, containing only about 10 billion stars compared to the Milky Way's few hundred billion. But it is close, and that proximity makes it one of the most studied galaxies in the sky. The Large Magellanic Cloud is also a laboratory. Because it is a separate galaxy, every star in it sits at roughly the same distance from Earth. That makes comparisons easier. You do not have to worry about one star being twice as far away as another and appearing dimmer for that reason alone. They are all at 160,000 light-years, give or take. So if one star looks brighter than another, it actually is brighter. That uniform distance has allowed astronomers to study the population of massive stars in the Large Magellanic Cloud with a precision that would be difficult to achieve in the Milky Way, where stars are scattered across tens of thousands of light-years of depth. The downside is that 160,000 light-years is still far. Even the largest, brightest stars in the Large Magellanic Cloud appear as faint points of light through a telescope, and if those stars happen to be surrounded by dust, they can be nearly impossible to study. WOH G64 was first identified in the 1970s by a team of astronomers led by Bengt Westerlund, along with Niels Olander and B. Hedin. They were conducting a survey of the Large Magellanic Cloud, cataloguing bright stars, and trying to identify the most massive and luminous objects in the galaxy. WHA stands for Westerlund, Olander, and Hedin. The number is just a catalogue entry. The star did not have a name. It still does not really. WOH G64 is just a label, a shorthand for the 604th object in their survey that happened to sit in a region they were studying. When they first noted it, they could tell it was bright, they could tell it was red, but they could not tell much else because the star was surrounded by something. A shell, a cloud, a thick envelope of material that was scattering and absorbing the light before it could reach their telescopes. For decades, WOH G64 sat in the catalogue as a curiosity. Astronomers knew it was there. They knew it was probably a red supergiant based on its color and brightness. But measuring its size, its temperature, its exact luminosity, all of that was difficult because the surrounding material distorted the observations. It was like trying to study a light bulb through frosted glass. You can see the glow, but you cannot see the details. The breakthrough came with infrared astronomy. Infrared light has a longer wavelength than visible light, which means it can pass through dust more easily. When astronomers pointed infrared telescopes at WOH G64, they started to see through the veil. They could measure the spectrum of the star itself, not just the scattered light from the dust. They could estimate the temperature, they could calculate the luminosity, and they could start to piece together just how large this object actually was. The numbers that came back were staggering. Current estimates place WOH G64's radius at about 1,540 times the radius of the Sun. Some older sources and secondary reports push that number higher, closer to 2,000 times the Sun's radius, depending on how you define where the star ends and the surrounding material begins. Either way, the scale is comparable to Scuti. If you placed WOH G64 at the center of our solar system, its surface would drift past Jupiter, possibly past Saturn, possibly farther. The star is enormous, bloated and shedding mass at a rate that suggests it is in the final stages of its life. And unlike Scuti, which sits relatively unobscured in the Milky Way, WOH G64 is buried inside a cocoon of its own making. The envelope surrounding WOH G64 is not a thin shell. It is a dense, thick ring of dust and gas that completely obscures the star in visible light. When you point an optical telescope at WOH G64, you do not see a star. You see a faint red glow from the dust cloud. The dust is heated by the star's radiation, and it re-emits that energy in the infrared. The cloud is so optically thick that the star itself is essentially invisible. Astronomers studying WOH G64 are not looking at the surface of the star. They are looking at the material that has been blown off the surface over the last few 100,000 years, piled up around the star like a fog bank. That material tells a story, and the story is one of extreme mass loss. Red supergiants shed mass. That is what they do. The outer layers are so loosely bound that the star's radiation pressure and thermal expansion push material away from the surface continuously. Most red supergiants lose mass at a rate of about 1/10,000,000th of a solar mass per year, which is already significant. WOH G64 is losing mass faster than that. Estimates vary, but some studies suggest it is shedding material at one of the highest rates ever measured for a red supergiant. One report described WOH G64 as among the strongest mass loss cases known. The exact rate is difficult to pin down because the dust obscures the measurements, but the sheer amount of material surrounding the star tells you that this object has been hemorrhaging mass for a long time. Why is WOH G64 losing mass so fast? The answer probably has to do with its luminosity. WOH G64 is extraordinarily bright. Current estimates place its luminosity at about 282,000 to 300,000 times the Sun's luminosity. That is slightly more than double the luminosity of Scuti. A star that luminous is pumping out an enormous amount of energy, and much of that energy is in the form of ultraviolet and infrared radiation. When that radiation hits atoms in the star's outer layers, it transfers momentum to them. The atoms get pushed outward. If the star is luminous enough, the outward push from radiation pressure can overcome gravity entirely. The material gets blown off the surface and drifts into space. For WOH G64, that process has been running for hundreds of thousands of years, possibly longer. The result is a thick, dusty envelope that extends far beyond the star's photosphere. The envelope is not spherical. Recent observations suggest it has structure. Some reports describe it as ring-shaped, a thick torus of material surrounding the star's equator. Other observations show asymmetries, clumps, and arcs, which suggest that the mass loss is not uniform. The star might be shedding more material from certain regions than others. It might be rotating, which would cause material near the equator to be flung outward faster than material near the poles. Or the star might have a companion, a binary partner whose gravitational influence is shaping the flow of gas and dust. There is evidence for a companion. Reports from recent infrared studies describe a blue object near WOH G64, possibly a hot, massive star orbiting the red supergiant. If that companion is real, and if it is close enough, it could be stirring up the envelope, creating spiral patterns and density waves in the surrounding material. The presence of a companion raises interesting questions. If WOH G64 is in a binary system, how did the two stars form? Did they form together from the same cloud of gas, or did one capture the other later? If they formed together, why is one a red supergiant and the other still a hot blue star? Stars in a binary system should be roughly the same age. If they are the same age, they should be at similar stages of evolution, unless one of them started with significantly more mass than the other. A more massive star evolves faster, so it would reach the red supergiant phase first, while its companion is still on the main sequence. That is possible. It is also possible that the blue object is not a companion at all. It might be a foreground or background star that just happens to appear close to WOH G64 in the sky. Sorting out the geometry requires more detailed observations, and those observations are difficult to make when the object you are studying is buried in dust. The dust itself is interesting. It is not just gas. It is solid particles, tiny grains of silicates and carbon that have condensed out of the gas blown off the star. When material leaves the surface of a red supergiant, it is hot, ionized gas. As it drifts outward and cools, atoms start sticking together. Carbon atoms link up to form chains and rings. Silicon and oxygen combine to form silicates, the same minerals that make up much of Earth's crust. Those molecules grow into larger and larger clumps until they become grains of dust, each one only a fraction of a micron across. The grains scatter and absorb light, which is why they obscure the star. But they also radiate in the infrared, which is how astronomers can study them. By measuring the infrared spectrum of the dust, you can determine what it is made of, how hot it is, and how far from the star it sits. For WOH G64, the dust shell extends far beyond the star itself. Some estimates place the outer edge of the shell at distances of several astronomical units from the star, possibly farther. That is a huge volume of space filled with material that used to be part of the star. The total mass of the shell is uncertain, but it could be several solar masses worth of gas and dust. That means WOH G64 has shed a significant fraction of its original mass. If the star currently weighs about 20 to 28 solar masses, which is the estimate from recent studies, and if it has shed several solar masses into the envelope, then it must have started with something like 30 to 40 solar masses or more. The exact number is uncertain because the mass loss rate has probably changed over time. Early in the star's life, when it was a stable main sequence star, the mass loss would have been negligible. Later, when it swelled into a red supergiant, the mass loss would have ramped up, and now, in the final stages of its life, the mass loss is extreme. The current mass of WOH G64 is another source of uncertainty. Early estimates, some of which still float around in older sources and on websites, placed the star at much higher masses. Some sources claimed 50 solar masses or more. More recent analyses, using better data and more sophisticated models, have revised that number downward to around 20 to 28 solar masses. That revision reflects a better understanding of how red supergiants evolve and how much mass they lose. But it also highlights how difficult these measurements are. You cannot put a star on a scale. You have to infer its mass from its luminosity, temperature, and evolutionary models. And if your models are wrong, or if your measurements are affected by the surrounding dust, your mass estimate will be wrong too. The temperature of WOH G64 is another interesting piece of the puzzle. For most of its catalogued history, the star appeared red, which suggested a surface temperature of around 3000 to 3500 Kelvin. That is typical for a red supergiant. But recent observations have reported something strange. The star appears to have changed color. Some reports describe WOH G64 as now appearing yellow rather than red. If that is true, it suggests the surface temperature has increased. A yellow star is hotter than a red star. A surface temperature increase could mean the star is contracting, or it could mean the outer layers are thinning as material is blown away, exposing deeper, hotter layers underneath. Either way, a color change is significant. Stars do not usually change color on human timescales. The fact that WOH G64 might have shifted from red to yellow over the span of a few decades suggests that the star is evolving rapidly. What does that mean for WOH G64's future? It could mean the star is transitioning out of the red supergiant phase and into something else, possibly a yellow supergiant, possibly a hotter, more compact object like a Wolf-Rayet star. If the star is shedding its outer hydrogen layers and exposing its helium-rich core, then it is following the same path that leads to a Wolf-Rayet phase, but it has not reached that stage yet. The spectrum still shows signs of hydrogen. The star is still relatively cool by Wolf-Rayet standards. It is in a transitional state, somewhere between a red supergiant and whatever comes next. The uncertainty in WOH G64's parameters is frustrating for astronomers, but also instructive. It shows how difficult it is to study stars that are far away and heavily obscured. Scuti, for all its size, is relatively easy to observe because it sits in the Milky Way and is not surrounded by a thick dust shell. WOH G64 is the opposite. It sits in another galaxy, 160,000 light-years away, and it is buried in dust. Every measurement is indirect. Every estimate depends on assumptions about the dust, the star's atmosphere, and the evolutionary models. Change one assumption, and the numbers shift. That does not mean the measurements are wrong. It means they have large uncertainties, and those uncertainties are honest. Science is not about having all the answers. It is about being clear about what you know and what you do not know. For WOH G64, there is a lot we do not know. One of the biggest unknowns is the star's progenitor mass. How heavy was WOH G64 when it first formed? 30 solar masses? 40? 50? The answer matters because it determines what the star will become. A star that started with 30 solar masses will end its life as a supernova, leaving behind a neutron star. A star that started with 50 solar masses will also go supernova, but it might leave behind a black hole instead. The boundary between those two outcomes is not sharp. It depends on how much mass the star loses before it explodes. If WOH G64 has already shed half its mass, then even if it started heavy, it might end up on the lighter side and leave a neutron star. Or it might collapse directly into a black hole without a supernova at all, a process called a failed supernova, where the core collapses so fast that the outer layers do not have time to bounce and explode. They just fall inward and disappear across the event horizon. Some models predict that stars in a certain mass range, roughly 25 to 30 solar masses after mass loss, are prime candidates for failed supernovae. If WOH G64 fits into that range, it might vanish without a bang, or it might not. Predicting the fate of an individual star is difficult because there are so many variables: the amount of mass loss, the rotation rate, the composition of the core, whether the star is in a binary system. All of those factors affect the outcome. WOH G64 could explode as a Type II supernova, the kind where hydrogen is still present in the outer layers, or it could strip away so much of its envelope that it explodes as a Type IB or IC supernova, where the hydrogen is gone. Or it could undergo some intermediate scenario, something messy and irregular that does not fit neatly into the classification scheme. The universe does not care about our categories. It does what the physics dictates, and sometimes the physics produces outcomes that surprise us. The discovery that WOH G64 is so heavily obscured came relatively late. For decades, astronomers knew the star was bright and red, but they did not fully appreciate how much material was surrounding it. Early observations in visible light missed most of the structure because the dust absorbs visible light efficiently. It was only when infrared telescopes became available that the full extent of the envelope became clear. Infrared light penetrates dust much more effectively than visible light. The longer wavelength means the photons can slip past the dust grains without being scattered or absorbed. By observing WOH G64 in the near-infrared and mid-infrared, astronomers could see through the envelope and start to map its structure. Modern infrared surveys have revealed that WOH G64 is not alone in having a thick dust shell. Many red supergiants in the Large Magellanic Cloud show similar features. The galaxy is full of massive dying stars surrounded by their own ejected material. What makes WOH G64 stand out is the sheer amount of material and the extreme size of the star underneath. Most red supergiants in the Large Magellanic Cloud swell to a few hundred solar radii. WOH G64 has swollen to more than 1,000. That puts it in the same class as Scuti and a handful of other extreme objects. Why WOH G64 got so large is unclear. It probably has to do with its initial mass, its composition, and the specifics of how it evolved. Stars with slightly different starting conditions can end up in very different places. WOH G64 seems to have hit the right combination of factors to produce an object of truly extreme size. Comparing WOH G64 to Scuti highlights the challenges of measuring stellar sizes. Scuti is closer, less obscured, and easier to study. WOH G64 is farther away, buried in dust, and harder to pin down. Both stars are pulsating variables, meaning their sizes change over time as they expand and contract. Both stars are shedding mass at high rates. Both stars are in the final stages of their lives, racing towards supernova. But the uncertainties in WOH G64's measurements are larger because of the dust. When you read that WOH G64 is 1,540 solar radii, or 2,000 solar radii, or whatever number a particular source gives, you have to remember that those numbers come with error bars. The true size could be 10 or 20% larger or smaller. That does not make the measurements useless. It makes them estimates, and estimates are what we have to work with when studying objects this extreme. The fact that WOH G64 sits in the Large Magellanic Cloud also gives us a unique perspective. The Large Magellanic Cloud is metal poor compared to the Milky Way. Metal, in astronomy jargon, means any element heavier than helium. The Large Magellanic Cloud has about half the metal content of the Milky Way. That difference affects how stars form and evolve. In a metal-poor environment, stars can grow larger because there is less dust and opacity in the gas clouds they form from. Less opacity means radiation can escape more easily, which allows the cloud to cool more efficiently, which allows it to collapse into larger clumps. The result is that the Large Magellanic Cloud produces a higher fraction of very massive stars than the Milky Way does. And those massive stars, when they reach the red supergiant phase, can swell to even larger sizes because they started with more mass. WOH G64 might be a product of that environment. It might have grown so large in part because it formed in a galaxy where conditions were just right to produce an extreme object. The Large Magellanic Cloud also gives us a preview of what the Milky Way will look like in a few billion years. The two galaxies are on a collision course. In about 2.5 billion years, the Large Magellanic Cloud will slam into the Milky Way. The collision will not be a physical crash. Galaxies are mostly empty space. The stars in both galaxies will pass through each other like two clouds of gnats interpenetrating. But the gas in both galaxies will collide, and that collision will trigger an enormous burst of star formation. Massive stars will form by the millions. Red supergiants like WOH G64 will become common. The night sky, if anyone is around to see it, will be full of giants. And then, a few million years later, those giants will start exploding. The Milky Way will be lit up by supernovae, one after another, enriching the galaxy with heavy elements and reshaping the structure of the interstellar medium. WOH G64 is a preview of that future. It is a glimpse of what happens when a massive star reaches the end of its life in a galaxy that is still young and metal-poor. The ring-shaped dust envelope around WOH G64 is also a clue to the star's rotation. If the star is rotating, centrifugal force would cause material near the equator to be flung outward faster than material near the poles. Over time, that would produce a flattened, disc-like or ring-like structure. Observations suggest that WOH G64's envelope is indeed flattened, which means the star is probably rotating. How fast it is rotating is unclear. Measuring the rotation speed of a star this far away and this obscured is difficult, but the structure of the envelope gives you indirect evidence that rotation is playing a role. If the star has a companion, the companion's gravity could also be shaping the envelope, pulling material into spiral arms, or creating asymmetries. Disentangling the effects of rotation and binary interaction is one of the challenges astronomers face when studying objects like WOH G64. The color change reported in WOH G64 is one of the most intriguing recent developments. If the star has shifted from red to yellow, it suggests the outer envelope is thinning. As the star sheds mass, the layers above the core get thinner and more transparent. Deeper, hotter layers become visible. The effective temperature, the temperature you measure at the photosphere, increases. The star looks bluer. If WOH G64 continues to shed mass at its current rate, it will eventually strip away most of its hydrogen envelope entirely. What remains will be a hot, compact core, possibly a Wolf-Rayet star, surrounded by a glowing nebula of its own making. That transformation, if it happens, will occur over the next few 100,000 years. For a star, that is a blink. For a human, it is incomprehensibly long. But it is happening. Right now, as you read this, WOH G64 is evolving. Layers are being blown away, the surface is moving inward, the core is contracting and heating, the star is racing toward an endpoint that could come at any moment or could take another million years. We do not know. We cannot know. All we can do is watch and measure and try to understand the process. The difficulty in observing WOH G64 is a reminder of how much we still do not know about the universe. We can send probes to other planets. We can measure gravitational waves from colliding black holes a billion light-years away. We can image the cosmic microwave background and peer back to the first few 100,000 years after the Big Bang. But a single star sitting 160,000 light-years away, surrounded by dust, can still hold mysteries that take decades to unravel. WOH G64 is not hiding on purpose. It is not trying to keep secrets. It is just sitting there, doing what dying stars do, and the dust it has blown off happens to be in the way. That dust is the result of the star's own evolution. It is the exhaust from the engine that has been running for millions of years, and it is also the veil that makes studying the engine so difficult. Infrared astronomy has been the key to unlocking WOH G64. Observations in the near-infrared and mid-infrared have allowed astronomers to see through the dust and measure the star's properties with greater accuracy than was possible in visible light. But even infrared observations have limits. The dust absorbs some infrared light too, especially at shorter infrared wavelengths. To get the clearest view, you need to observe at longer wavelengths in the far infrared or even in the submillimeter range. Those observations require specialized telescopes and detectors, and they are expensive and time-consuming to carry out. WOH G64 is a high-priority target for those kinds of observations because it is one of the most extreme examples of a dust-enshrouded red supergiant. But telescope time is limited, and there are many other objects competing for attention. Progress is slow. The envelope around WOH G64 also contains clues to the star's history. By analyzing the composition of the dust, astronomers can determine what elements the star has been fusing in its core and blowing off into space. Carbon-rich dust suggests the star has been fusing helium into carbon and dredging that carbon up to the surface. Silicate-rich dust suggests the star is blowing off material from deeper layers, where oxygen and silicon are more abundant. The ratio of different elements in the dust tells you about the sequence of fusion reactions that have occurred in the core. It is like reading a star's biography, written in the chemical fingerprints of the material it has shed. WOH G64 is also a reminder that the largest stars are not the most massive. WOH G64 weighs somewhere between 20 and 28 solar masses, depending on which estimate you trust. That is a fraction of the mass of R136A1, which weighs close to 200 solar masses, but WOH G64 is much larger in radius. The disconnect between mass and size is a feature of late-stage stellar evolution. When a star swells into a red supergiant, it is no longer a compact, dense object. It is a diffuse, bloated shell of gas held together by a weak gravitational grip. The mass is spread over such an enormous volume that the density drops to almost nothing. Scuti and WOH G64 are both examples of stars that have reached the extreme end of that process. They are as large as a star can get without falling apart entirely, and they are teetering on the edge. How much larger can a star get? That question leads directly into the next part of this story. WOH G64 and Scuti represent the current known extremes. But are they the limit? Is there a hard boundary, a maximum size beyond which a star cannot swell no matter how massive it starts or how much it sheds? Or is there room for something even larger? Something we have not found yet simply because it is rare and difficult to observe? The answer depends on the physics of stellar structure, the balance between radiation pressure and gravity, and the quirks of stellar evolution that allow some stars to grow to absurd sizes while others stay relatively compact. The edge of existence, the absolute limit of how big a star can be, is not a number you can look up in a textbook. It is a question that requires looking at the physics, the observations, and the gaps between what we know and what we are still trying to figure out. The question sitting at the end of all this, the one that ties Scuti and Shrouded M64 and every other bloated giant together, is simple. How big can a star actually get? Not how big have we found, how big is allowed? Where is the line? Where does physics finally put its foot down and say, no, you cannot swell any further? This is the edge. This is where the universe stops letting you exist as a single coherent object. That line exists. It has to. Because if there were no limit, stars would just keep expanding forever. And we would see objects the size of solar systems, objects the size of galaxies, objects so diffuse that calling them stars would be meaningless. We do not see that. What we see instead are stars like Scuti and WOH G64, sitting right at the edge of what seems physically possible, flickering and pulsing and shedding mass like they are trying to tear themselves apart but have not quite managed it yet. They are the boundary cases, the outliers, the objects that exist only because a very specific set of conditions lined up in exactly the right way to allow them to swell this large without collapsing or exploding first. And studying them is how astronomers figure out where the limit actually is. The first thing to understand is that there is no single limit. There is not one magic number that applies to all stars. The maximum size a star can reach depends on its mass, its composition, its age, and how fast it is losing material. A star that weighs 10 solar masses can swell to a certain size before radiation pressure blows the outer layers away. A star that weighs 30 solar masses can swell larger because it has more gravity holding it together. But it also burns hotter and brighter, which means it is pumping out more radiation, which means the radiation pressure pushing outward is stronger. The two effects fight each other. More mass gives you more gravity. More gravity allows a larger envelope. But more mass also gives you more luminosity. More luminosity gives you stronger radiation pressure. And if the radiation pressure gets strong enough, it tears the envelope apart no matter how much gravity is trying to hold it together. The balance between those two forces is what determines the maximum size. For a red supergiant, the limit seems to sit somewhere around 2,000 solar radii, give or take a few hundred. That is roughly the size of WOH G64 at the upper end of its estimates. Scuti sits just below that, at around 900 to 1,500 solar radii, depending on which measurement you trust. Betelgeuse, one of the most studied red supergiants in the sky, sits at about 700 solar radii. All three stars are in the same ballpark. All three are near the upper limit, and all three are unstable. They are pulsating, they are shedding mass. They are not going to stay this large forever. In a few 100,000 years, maybe less, they will have shed so much of their outer envelopes that they will shrink. They will transition into hotter, more compact objects, and eventually they will explode. The fact that all three stars are so close in size despite being different masses and sitting in different galaxies tells you that the limit is real. If stars could swell larger than 2,000 solar radii, we would see examples of stars doing that. We do not. The biggest stars we have found, after decades of searching and measuring, all cluster in the same narrow range. That clustering is not a coincidence. It is physics asserting itself. It is the universe telling us that this is as big as a star can get before the structure becomes so unstable that it cannot hold itself together anymore. But the limit is not sharp, it is fuzzy. There is no bright line where a star at 1999 solar radii is stable and a star at 2001 solar radii immediately flies apart. The transition is gradual. As a star approaches the limit, it becomes more and more unstable. The pulsations get stronger, the mass loss accelerates, the envelope starts to break up into clumps and shells, the star flickers and dims and brightens irregularly. It is fighting a losing battle against its own energy output, and eventually it loses. The outer layers drift away, the envelope thins, the star contracts. And what you are left with is a smaller, hotter object sitting at the center of a glowing nebula of its own discarded guts. Scuti is in that fight right now. So is WOH G64. So is Betelgeuse, though Betelgeuse is slightly smaller and slightly more stable. All three stars are losing mass at rates high enough that within a few 100,000 years they will look completely different. The envelopes will be gone. The surfaces will have moved inward. The temperatures will have climbed, and the stars will have transitioned into the next phase of their lives, whatever that phase turns out to be. For Scuti, the next phase might be a yellow supergiant, a slightly hotter and slightly smaller version of what it is now. Or it might skip that phase entirely and go straight to Wolf-Rayet, exposing the core and blowing a wind at thousands of kilometers per second. For WOH G64, the color change that has been reported in recent observations suggests the transition might already be starting. The star has shifted from red to yellow, which means the surface temperature is climbing. That could be a sign that the outer layers are thinning and deeper, hotter layers are becoming visible. Or it could be a sign that the entire structure is contracting. Either way, the star is evolving, and the evolution is happening on timescales short enough that astronomers can watch it. That is one of the most exciting things about studying these extreme stars. They are not static, they are changing. If you could sit in a time machine and watch Scuti for the next million years, you would see it transform. You would see the envelope puff up and contract as the star pulsates. You would see shells of gas blown off the surface, drifting outward and cooling into dust. You would see the star brighten and dim as the pulsations shifted its surface area. And eventually, you would see the whole thing collapse inward, shrink, heat up, and transition into something new. The show would be slow by human standards, but it would be a show, a front-row seat to stellar evolution in action. The uncertainty in the size measurements is frustrating, but it is also informative. When you read that Scuti is 909 solar radii in one paper and 1700 solar radii in another, that is not because one team is incompetent. It is because measuring the size of a star this large and this far away is genuinely difficult. The star does not have a sharp edge. The outer layers are so diffuse that they fade gradually into the surrounding space. Different wavelengths of light come from different layers. Measure the star in visible light, and you are seeing the photosphere, the layer where the gas becomes opaque. Measure it in infrared, and you are seeing the cooler, dustier layers farther out. Measure it in radio waves, and you are tracing the ionized gas even farther out. All of those measurements are correct. They are just measuring different things. So when you ask how big Scuti is, the answer depends on what you mean by size. The photospheric radius is probably around 900 solar radii. The dust shell might extend to 1500 solar radii or more. Both numbers are real, both numbers tell you something about the star, and both numbers have uncertainties because the star is pulsating and the layers are moving. The other challenge is distance. Scuti sits somewhere between 5,900 and 9,500 light-years from Earth, depending on which distance estimate you use. That is a huge range. The farther the star is, the larger it must be to appear as bright as it does from Earth. The closer it is, the smaller it can be. Early estimates assumed the star was farther away, which led to larger size estimates. Newer measurements, using better data from the Gaia satellite, suggest the star is closer, which brings the size estimate down. The revision is not a correction in the sense that someone made a mistake. It is an improvement. Science is iterative. You make the best estimate you can with the data you have, then you gather better data and refine the estimate. The fact that the numbers change over time is not a flaw in the process. It is the process working as intended. The same uncertainty applies to WOH G64. The star sits in the Large Magellanic Cloud, which is about 160,000 light-years away. That distance is well known, which helps. But the star itself is buried in a thick shell of dust, and that dust distorts the observations. You are not seeing the star directly. You are seeing the glow from the dust, heated by the star's radiation. Inferring the properties of the star from the properties of the dust requires a model, and models have assumptions. Change one assumption, maybe the opacity of the dust or the geometry of the shell, and the numbers shift. The current best estimate places WOH G64 at about 1540 solar radii. Some older sources push that number to 2000 or higher. The truth is probably somewhere in between, but the exact number matters less than the fact that WOH G64 is unquestionably one of the largest stars we have ever found. It is in the conversation, it is at the edge, and it is shedding mass at one of the highest rates ever measured for a red supergiant. Betelgeuse, by comparison, is easier to study because it is closer and less obscured. Betelgeuse sits only about 550 light-years from Earth, which is practically next door by galactic standards. It is bright enough to be visible to the naked eye, sitting as the red shoulder of Orion, one of the most recognizable constellations in the sky. And because it is so close and so bright, astronomers have been able to measure its size with a precision that is not possible for more distant stars. Betelgeuse has a radius of about 700 solar radii, give or take 50 depending on the pulsation phase. That makes it smaller than Scuti and WOH G64, but still enormous by any reasonable standard. If you placed Betelgeuse where the Sun is, its surface would extend past the orbit of Mars, well into the asteroid belt. It is a giant, just not the largest giant. The reason Betelgeuse keeps coming up in these discussions is not because it holds the record for size. It does not. It comes up because it is the largest star we can study in detail. We can measure its surface features. We can watch convection cells, giant bubbles of hot gas rising and falling, each one larger than the orbit of Mercury. We can track its pulsations. We can measure its mass loss. We can do all of this because Betelgeuse is close enough that modern telescopes can resolve it as a disk rather than a point of light. That level of detail is not available for Scuti or WOH G64. Those stars are too far away. They appear as points even through the most powerful telescopes. So Betelgeuse becomes the reference point, the benchmark, the star that tells us what a red supergiant looks like up close. And what it tells us is that these stars are messy, chaotic, and barely holding themselves together. The debate over which star is the largest is ongoing, and probably will not be settled anytime soon. Part of the problem is that the measurements keep changing as new data comes in. Part of the problem is that the stars themselves are changing. They are pulsating, they are shedding mass, they are not static objects sitting at fixed sizes. And part of the problem is that the definition of size is not as simple as it seems. Do you measure the radius of the photosphere? Do you measure the extent of the dust shell? Do you measure the boundary where the stellar wind transitions into the interstellar medium? All three definitions give you different numbers, and all three definitions are defensible. What is not debatable is that these stars represent the extreme end of stellar evolution. They are as large as stars can get. They are at the edge of existence. And studying them tells us something fundamental about the limits of what the universe allows. Stars are governed by a delicate balance between gravity pulling inward and pressure pushing outward. For most of a star's life, that balance is stable. The star sits on the main sequence, fusing hydrogen, glowing steadily, and not doing much of interest. Then the hydrogen runs out. The balance breaks. the core contracts. The outer layers expand, and the star enters a phase where the structure is constantly shifting, constantly adjusting, constantly trying to find a new equilibrium that does not exist. Red supergiants are stars that have lost that equilibrium. They are inflated, unstable, and doomed. And the largest red supergiants, the ones we have been talking about, are the most unstable of all. The fact that stars this large exist at all is remarkable. The radiation pressure from a star like Scuti should be strong enough to blow the outer layers away entirely. The fact that the layers are still there, still clinging to the core, tells you that gravity is barely winning. But it is winning. For now. The outer layers are held together not by a strong gravitational grip, but by inertia. They are drifting outward slowly, but they have not reached escape velocity yet. The star is losing the fight, but the fight is not over, not yet. One of the key insights from studying these stars is that size and mass are not the same thing. Scuti weighs somewhere between 7 and 10 solar masses. That is a fraction of the mass of R13601, which weighs close to 200 solar masses. But Scuti is 30 times wider. The disconnect between mass and size is a feature of late-stage stellar evolution. When a star swells into a red supergiant, it is no longer a dense, compact ball of gas. It is a diffuse, bloated shell held together by a weak gravitational field. The mass is spread over such an enormous volume that the density drops to almost nothing. The outer layers of Scuti are less dense than the best vacuum ever created in a laboratory on Earth. You could fly a spaceship through them and not notice you were inside a star until the temperature started climbing. This is why the largest stars by radius are not the largest stars by mass. The two categories are almost mutually exclusive. The most massive stars, the ones like R13601, are compact, dense, and incredibly hot. They are pumping out energy at a rate that prevents them from swelling. Their luminosity is so high that radiation pressure pushes the outer layers away faster than they can accumulate. The result is a star that weighs 200 solar masses, but is only 30 or 40 times the Sun's radius. Contrast that with Scuti, which weighs 10 solar masses but is 900 times the Sun's radius. Scuti has swollen precisely because it is not that massive. Its gravity is weak enough that the outer layers can expand without being held in check, and its luminosity, while still enormous by human standards, is not high enough to blow the envelope away immediately. The star is in a sweet spot where it can swell to an extreme size and maintain that size for a few 100,000 years before the mass loss finally thins the envelope enough to cause a contraction. The ultimate fate of these stars is not in question. They are all going to explode. Red supergiants that start with masses above about 8 solar masses end their lives as supernovae. The core runs through its fuel, fusing hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into neon, neon into magnesium, magnesium into silicon, and finally silicon into iron. Iron is the end of the line. Fusing iron does not release energy, it absorbs energy. So once the core is made of iron, there is no more fuel, no more outward pressure, nothing to hold the core up. Gravity wins. The core collapses in less than a second. The collapse is so fast that the outer layers do not have time to react. They are still falling inward when the core reaches nuclear density and rebounds. The rebound sends a shockwave racing outward through the star at a significant fraction of the speed of light. When the shockwave reaches the surface, the star explodes. The energy released in that explosion is roughly equal to the total energy the Sun will produce over its entire 10 billion year lifetime, except it all happens in a few weeks. For Scuti, the explosion will be a Type II supernova, the kind where hydrogen is still present in the outer layers. The spectrum of the supernova will show strong hydrogen lines because the exploding star still has most of its hydrogen envelope intact. For WOH G64, the outcome might be different. WOH G64 is shedding mass at such a high rate that by the time the core collapses, the hydrogen envelope might be mostly gone. If that happens, the supernova will be a type I or type IC, where the hydrogen lines are weak or absent. The explosion will be just as energetic, but the spectrum will look different because the outer layers have been stripped away. There is another possibility, one that is less dramatic but equally fascinating. Some massive stars, particularly those in a narrow mass range after accounting for mass loss, might not explode at all. Instead, they undergo a failed supernova. The core collapses. The shock wave starts moving outward, but the shock wave stalls. It loses energy as it pushes through the dense outer layers. It never makes it to the surface. The outer layers, instead of being blown off, just fall inward and disappear across the event horizon as the core collapses into a black hole. From the outside, you would see the star dim and vanish. No explosion, no bright light show. Just a quiet fade as the entire star gets swallowed by the black hole it creates. Astronomers have found a few candidate failed supernovae, stars that were there 1 year and gone the next with no supernova detected. If Scuti or WOH G64 undergoes a failed supernova, we might never know. The star would just vanish from the sky. The more common outcome is a successful supernova followed by a neutron star or a black hole. For stars in the mass range of Scuti and WOH G64, the remnant is probably a neutron star. A neutron star is what you get when the core collapses and the density gets so high that protons and electrons merge into neutrons. The result is an object about 20 kilometers across, weighing more than the Sun, held up by neutron degeneracy pressure. Neutron stars are the densest objects in the universe that are not black holes. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravity at the surface is so strong that light gets bent into strange paths. Time runs slower at the surface than it does farther away, and the magnetic fields, in some cases, are the strongest magnetic fields known to exist anywhere. If the core is heavy enough, even neutron degeneracy pressure cannot hold it up. The core collapses past the point where neutrons can resist compression. It becomes a black hole. The boundary between a neutron star and a black hole sits somewhere around 3 solar masses for the core, though the exact number depends on the equation of state of nuclear matter, which is still not fully understood. If Scuti started with a mass of about 30 solar masses and has shed most of it, the core at the time of collapse might weigh 10 or 15 solar masses. That is enough to form a black hole. The black hole left behind would not be large by black hole standards. It would weigh maybe 5 to 10 solar masses, far smaller than the supermassive black holes sitting at the centers of galaxies. But it would still be a region of space-time so warped that nothing, not even light, could escape. The remnants of these stars, whether neutron stars or black holes, will outlive everything else in the universe. Neutron stars cool over billions of years, fading from white-hot to red to black. But they never truly disappear, they just stop glowing. Black holes evaporate through Hawking radiation, but the process is so slow that a 10 solar mass black hole will take longer than the current age of the universe to evaporate completely. Long after the last stars have burned out, long after the galaxies have drifted so far apart that they can no longer see each other, the remnants of stars like Scuti and WOH G64 will still be out there drifting through the dark. The broader cosmic perspective offered by these stars is humbling. Scuti weighs 10 solar masses and is 900 times the Sun's radius. If you placed it in our solar system, it would swallow everything out to Jupiter. The entire inner solar system, every planet you learned about in school, would be inside the star, and yet Scuti is not even close to being the most massive star. It is not the brightest star. It is not the hottest star. It is just the most inflated star. It has reached the edge of how large a star can get, and it is holding that position through a combination of luck, timing, and physics that happens to allow an object this absurd to exist for a few 100,000 years before collapsing or exploding. That absurdity is what makes these stars worth studying. They are not typical, they are not average, they are outliers, but outliers are where you learn the most. When you study the average case, you confirm what you already know. When you study the extreme case, the one that is barely possible, the one that sits right at the edge of what the universe allows, you learn where the boundaries are. You learn what happens when gravity and radiation pressure are locked in a fight that neither can decisively win. You learn what a star looks like when it is tearing itself apart but has not quite managed it yet. And you learn that the universe is stranger, more varied, and more extreme than any model could predict. The advances in observational techniques over the last few decades have pushed the boundaries of what we can measure. Infrared astronomy has allowed us to see through the dust shells surrounding stars like WOH G64. Interferometry has allowed us to measure the angular sizes of stars with a precision that was unthinkable 50 years ago. The Gaia satellite has given us better distances to thousands of stars, which has allowed us to refine size estimates and luminosity calculations. And new telescopes like the James Webb Space Telescope are giving us the ability to study stars in other galaxies with the same level of detail we used to reserve for stars in the Milky Way. Every new instrument, every new technique pushes the limit of what we can observe, and every new observation refines our understanding of where the edge of existence actually is. The title of largest star will keep changing. New measurements will come in, new stars will be discovered, old estimates will be revised. That is how science works. The question is not settled. It might never be fully settled because the stars themselves are changing and the measurements have uncertainties. But the question is worth asking. How big can a star get? Where is the limit? What happens at the edge? And what does it tell us about the universe that these objects exist at all? The answer is that the universe allows stars to swell to roughly 2,000 times the radius of the Sun before the structure becomes so unstable that it cannot hold together anymore. That is the limit. That is the edge. Scuti and WOH G64 and a handful of other red supergiants are sitting right at that edge, flickering and pulsing and shedding mass, racing toward an endpoint that could come tomorrow or could take another 1,000,000 years. We do not know when. We cannot know when. All we can do is watch and measure and try to understand the process. And in doing that, in studying these monstrous stars that defy every intuition about what a star should look like, we are learning something fundamental about the nature of matter, energy, gravity, and light. We are learning what the universe allows, and we are learning that the limits are higher, stranger, and more extreme than anyone expected. So here we are, at the end of a journey that started with the Sun, an average star by every measure that matters, and ended with objects so large they break intuition. Stars that could swallow solar systems, stars that weigh less than some objects a fraction of their size, stars that are held together not by a strong gravitational grip, but by inertia and luck. drifting at the edge of what physics allows before the whole structure comes apart. Scuti and WOH G64 are not the final word, they are the current word. The largest stars we have found so far, sitting at roughly 2,000 solar radii, pulsing and flickering and shedding mass like they are trying to tear themselves apart, but have not quite managed it yet. In a few 100,000 years, they will look completely different. The envelopes will be gone, the surfaces will have moved inward, the stars will have transitioned into something hotter, smaller and more violent, and eventually they will explode or collapse or vanish, leaving behind neutron stars or black holes that will outlive everything else in the universe. The fact that these objects exist at all is remarkable. The fact that we can measure them, study them, and argue about which one is larger is a testament to how far astronomy has come. But the deeper lesson is not about size, it is about limits, about what the universe allows and what it does not, about the line between stable and unstable, between structure and chaos, between a star